Never before in human history have we been richer, more advanced, more powerful. And yet, we feel overwhelmed in the face of rapid climate change. It seems simple on the surface. Greenhouse gases trap energy from the sun and transfer it to our atmosphere. This leads to warmer winters, harsher summers. Dry places become drier and wet places wetter. Countless ecosystems will die while the rising oceans swallow coasts and the cities we build on them. So why don't we just prevent all of that? Well, it's complicated. The public debate about stopping rapid climate change often focuses on a few key features like coal plants, cars, or burping cows. And so the solutions are often simplistic. Rows of solar panels, biking to work, something sustainability. And a huge talking point is personal responsibility. How you should change your lifestyle to prevent rapid climate change, which we'll find out together in the next few minutes. This is one of those videos where we want to encourage you to watch to the end, because to discuss real, doable solutions, we first need to understand the problem. A fuller picture. Modern industrial society, as we constructed it in the last 150 years, is inherently destructive to the planet. Basically, everything we do to make our lives easier, safer, and more comfortable is making things worse for the biosphere. The food we eat, the streets we walk on, the clothes we wear, the gadgets we use, the way we move around, and the pleasant temperatures we artificially create around us. While most people know about the serious impact of energy, beef, cars, and planes, many major polluters are barely ever talked about. The emissions leaking out of landfills are as significant as the emissions of all the jets in the air. More CO2 is released to run our homes than from all cars combined. And the emissions produced when making a new car is equivalent to building just 2 meters of road. So it is nice to switch to electric cars, but they won't solve anything if we keep building roads the same way. Fixing one small part of the industrial system is not enough. Each of the many different parts needs its own solution, and many of them aren't straightforward. But even where we know what to do, just because a solution exists doesn't mean we're able or willing to implement it. There are many grey areas in the fight against rapid climate change. The most prominent one is the divide between rich and poor. Emissions versus poverty. There is a clear connection between the prosperity of a nation and its carbon emissions. In other words, richer people tend to cause more emissions. So the key to fixing climate change is simply for the world's richest to cut back on their extravagant lifestyles, right? While this would help, it wouldn't make the problem go away. This is because 63% of global emissions come from low to middle income countries. Countries where most people are not living extravagantly but are trying to escape poverty at worst and achieve a comfortable lifestyle at best. The unfortunate reality is that currently, escaping poverty and becoming middle class creates unavoidable emissions. So asking developing countries to cut emissions just looks like an attempt to keep them down. It's very hard to argue that a region should protect their primeval forests and spend money on solar panels instead of burning wood when it can't meet basic needs for significant parts of its population. But cutting back is not a popular demand, especially if the countries making these demands got rich by causing environmental damage in the past. So for billions of people, more emissions are a good thing, personally. When we forget about this, we tend to propose unworkable solutions. Take concrete. 8% of CO2 emissions are released by the concrete manufacturing industry. Okay, cool. Stop using concrete, right? But right now, concrete is also a cheap and easy way for growing populations in developing countries to build affordable housing. And there are many examples like that. Even rich countries aren't immune from disagreeing about rapid climate change solutions. Banning coal, gas, and oil from the energy mix is slowed down by heated discussions about what should replace them. Citizens can be strictly against nuclear power, but also oppose wind or solar infrastructure in their backyards. In principle, all of these issues can be overcome, but there are things we don't currently know how to overcome. The most problematic one is food. Emit or die. We will soon need to feed 10 billion people, and we don't know how to do that without emitting greenhouse gases. Because of the nature of modern food production that requires fertilizers or manure, it's impossible to have zero-emissions food. Rice alone emits so much methane each year that it practically equals the emissions of all the air traffic in the world. What's worse is that the foods we like the most emit the most. 57% of food emissions come from animal-based foods, although they make up only 18% of the world's calories and 37% of its protein. And as people across the world grow richer, they want more meat. Traditional diets in most cultures were primarily plant-based with a little meat on top. But with the rise of industrial-style meat production and factory farming, meat has become a staple food, a regular indulgence in developed countries and a symbol of status and wealth in developing countries. Today, about 40% of the world's habitable land is used for meat production in some form or another, the size of North and South America combined. This is land we could otherwise allow native ecosystems to regrow, like forests in the Amazon, and suck carbon out of the atmosphere, but instead, most of it is used to feed animals. The available solutions are uniquely able to make everybody on the political spectrum, rich or poor, unhappy. Meat is highly emotional, and there are a lot of whataboutism arguments floating around, like comparing it to the worst sources of emissions. In the end, it's pretty simple. Eating less meat alone won't stop climate change, but we also can't stop climate change without eating less meat. The same holds true for other things that are less crucial to our survival, but frankly not realistic to make go away, like air travel, overseas shipping, mining, and the production of devices that play YouTube videos. So what does this mean? Do we need to give up our way of life, and can the poor never achieve it? Can't some technology save us so we can continue to drive our big cars and eat meat every day? Solutions versus expenses. In principle, this technology already exists. Direct air capture of CO2 draws carbon dioxide from the air so that it can be stored underground or transformed into products. So why aren't we implementing it in every industry everywhere? Because with the technology we have right now, this would cost some $10 trillion per year, or half the United States GDP. This money has to come from somewhere, and currently no one is offering it. Just dumping these costs on massive polluters like steel mills and coal power stations would double the cost of their products, and so these industries that operate on very tight profit margins would go bankrupt. Getting the government to pay for it seems logical, but a lot of state resources are actually tied up doing the opposite, like subsidizing oil and gas, which seems counterintuitive but follows clear incentives. By artificially keeping fuel prices low, shipping and everyday goods are kept artificially cheap too, which has a major social impact on billions of people around the world. That creates political lobbies and incentives that perpetuate a cycle that makes it so hard to stop fossil fuel production. Meanwhile, very costly solutions for a far-off problem, like carbon capture, seem like they can wait, as technically nobody benefits from it right now. Some argue that a move away from capitalism is the only solution to this mess. Others insist that markets should be even freer without any interventions like subsidies, and some suggest that we need what's referred to as degrowth, and to cut back as a species overall. But the truth is, at least as of now, no political system is doing an impressive job at becoming truly sustainable, and none have really done so in the past. We also don't have the time to figure this out and do a lot of experiments. We must implement solutions now, not just to halt the release of all possible greenhouse gases, but also to start reducing the amount of CO2 in the air. It's too late to just mend our ways, we have to actively correct our past mistakes. With every year we waste, more extreme changes will be unavoidable. Okay, let's take a deep breath. Rapid climate change and the world we live in are complicated, so here is where you, dear viewer, come in again. Could you please fix the climate? A narrative of our time is that we are all responsible for rapid climate change, that everyone needs to play their part. Why don't you buy a new electric car? Why don't you replace your gas stove with an electric one? How about you double glaze your windows, stop eating meat, and switch off your lights? Shifting responsibility from the largest carbon emitters to the average person, you, is much easier to do than solving problems. There's an extra bonus if solving rapid climate change sells a new product. If you don't have the money or time for these things, you should feel bad. It's an effective message because it's true. The quickest way to cut CO2 emissions would be if all rich populations on Earth drastically changed their lifestyles and if the people on the rise would not seek to achieve it, favoring the climate over comfort and wealth. If you're able to watch this video, that includes you. But we've just witnessed a global experiment in staying at home, not using transport, and consuming less during the coronavirus pandemic. And all it did was reduce CO2 emissions by 7% for 2020. Asking average people to solve rapid climate change breaks down when we look at the scale of the problem. Personal contributions towards reducing greenhouse gas emissions are nice, but they are dwarfed by the systemic reality of global emissions. The concept of your personal carbon footprint was popularized by the oil producer BP in a 2005 ad campaign. Arguably one of the most effective and sinister pieces of propaganda that still seriously distracts all of us from the reality of the situation. If you eliminated 100% of your emissions for the rest of your life, you would save 1 second's worth of emissions from the global energy sector. Even the most motivated person can't even make a tiny dent. When we put together the dangers of rapid climate change, the scale of emissions and the lack of consensus over how to solve it, the challenge seems insurmountable. It can cause decision fatigue and moral licensing where you no longer feel bad about behaving in a counterproductive way. We have struggled a long time with this, which is why this video took us so long to make. So, what can you actually do? There are many different takes, and they are passionately discussed. We don't know who's right, so we can only offer you the Kurzgesagt perspective and opinion. Opinion part. What can you actually do? We need a different way to think and talk about rapid climate change. An all-encompassing systemic approach, nothing less than changing the fundamentals of our modern industrial societies. As discussed in frustrating length, the personal responsibility angle is overplayed. For systemic changes in technology, politics, and the economy of this magnitude, we need to influence the people at the levers. Politicians need to know and feel strongly that the people care, that their own success depends on tackling rapid climate change. When governments and local politicians are reluctant to change laws that affect their biggest tax contributors or campaign donors, we need to vote them out and vote in people who respect science. We need to hold them accountable for implementing the most effective climate change strategies. Not waste our time with things like banning plastic straws, but by moving the big levers: food, transportation, and energy, while not forgetting the smaller ones like cement or construction. When industries fight against changing their ways for fear of losses or in an honest attempt to protect their own, we need politicians to change the laws and incentivize the deployment of existing technologies and massively invest in innovation for the fields where we don't have great solutions yet. There's no reason that the profit interests of industries could not match the need to reduce carbon emissions as much as possible. And if they still don't cooperate, harsh punishments and regulation need to force or bankrupt them. It's still unrealistic that change of that scope can be forced onto a worldwide economy quickly enough, because many low-carbon technologies still need a lot of time and research, which means they're expensive. But more companies will make more efficient carbon capture systems, tasty meat alternatives, better batteries, cement alternatives, and so on if there's a clear and growing demand. And if you're affluent enough, you can do your part by investing in these things right now while they're still expensive. These are the mechanisms that will drive the prices down later on. So this is basically what you can do. Vote at the ballot, vote with your wallet. There are too many opposing interests and complicated grey zones. In the end, if we truly get the systemic change we need, everybody will be unhappy about some aspect of it. Only if we all accept that some solutions will have negative impacts for us can we have an honest conversation and make progress. Everybody will be a little unhappy, and that's okay. This is the best you can do. You can deal with the reality of the situation and promote your priorities through your behavior and your actions. And while you do so, you can eat less meat, fly less, or get an electric car. Not because you should feel guilty if you don't, or because you naively believe that you alone can stop rapid climate change, but to do your tiny, tiny part for the systemic change we need. The Earth is a gigantic ball of semi-molten rock with a heart of iron as hot as the surface of the Sun. Titanic amounts of heat left over from its birth and the radioactive decay of trillions of tons of radioactive elements find no escape but up. Currents of rock spanning thousands of kilometers carry this energy to the surface. Earth's crust is the only thing in their way. It feels solid to us, but it's only a fragile barrier, an apple skin around a flaming behemoth. True apocalypses can break through and unleash eruptions tens of times more powerful than all of our nuclear weapons combined, subjecting the climate to centuries worth of change in a single year, while drowning continents in toxic ash and gases. Supervolcanoes. How big can they get? And will they put an end to humanity? Volcanoes. There are many types of volcanoes, from towering mountains to lava domes, but they have two main sources. The first is at the boundaries between tectonic plates, the pieces of the crust that cover the Earth like a giant jigsaw puzzle. There are 7 major tectonic plates and dozens of smaller ones, drifting against each other at up to 15 centimeters per year. This sounds slow, but on geological timescales, it is a titanic struggle over who gets to stay on the surface. The winning plate crumples into a new mountain range, while the loser is shoved underneath into an ocean of hot rock at 1,300 degrees Celsius, the asthenosphere. The temperature here is enough to melt rock into a liquid, but the insane pressures of all that mass keep it a superheated solid. Tectonic plates are usually in contact with water for thousands of years and absorb some of it. When they're submerged into the hot underworld, this water triggers chemical transformations that allow tiny portions to melt into magma. Liquid magma is less dense than solid rock, so it rises to the surface in furious bubbles that accumulate in sponge-like reservoirs right under the crust. If enough magma accumulates, it becomes powerful enough to pierce through the crust, which we experience as volcanoes. This happens under the winning plate, like a revenge attack by the loser before it's erased forever. The second main source of volcanoes are thought to be mantle plumes. These are columns of abnormally hot rock that rise all the way from the planet's core mantle boundary to the surface. Much less is known about them, but in a way, it's as if the Earth's mantle has weather patterns and mantle plumes are a little like hot air rising to form storm clouds. Storms hundreds of millions of years old, made of rock circulating at a rate of a few millimeters per month. They don't care about the motion of tectonic plates, so they can break the crust to create volcanoes in the middle of nowhere that stubbornly stay active as the crust shifts around them. The volcanic boom meter. Scientists love to put big booms on a scale and came up with a logarithmic scale that measures the volume ejected during an eruption. The Volcanic Explosivity Index, or VEI. Simply put, it starts really small and gets very big very quickly. A VEI-2 eruption would fill 400 full Olympic swimming pools with lava. We have around 10 of these per year. At VEI-3, we already see devastating effects, like the eruption of the Semeru volcano in 2021 that destroyed thousands of homes in Indonesia. At VEI-5, we see catastrophic amounts of materials, cubic kilometers of debris, equivalent to an entire lake of molten rock blasted into the air. Like the 2022 Hunga Tonga Hunga Hapai eruption that sent a shockwave around the globe many times and created ocean-wide tsunamis. At a VEI of 6, an eruption can change the world. In 1883, the Indonesian island volcano Krakatoa erupted nearly continuously over the course of 5 months. One of those eruptions blew it apart, producing the loudest sound recorded in history, 10 trillion times louder than a rocket taking off, heard halfway around the world. 30-meter-high tsunamis swept away nearby populations, and so much gas and ash were released that global temperatures cooled by nearly 0.5 degrees Celsius. Red, dusty sunsets followed for many years. At VEI-7, we get supercolossal eruptions, millennium-defining events that human civilization has only encountered a handful of times. Mount Tambora was a 4,300-meter high mountain until it exploded in 1815 and released 400 times more energy than the Tsar Bomber. 140 billion tons of ash and dust were shot halfway to space before smothering the world's skies, turning them a sickly yellow. There was no summer the following year, crops died, and over 100,000 people perished. This is the dreadful potential of volcanic eruptions, with famines across the other side of the world and even centuries-long cold periods being attributed to them. Okay, but what's a supervolcano? The term supervolcano is a media invention and not a scientific term. The main issue with them is that not every eruption from a supervolcano is a supereruption. What makes supervolcanoes special is that they've been waiting to erupt for hundreds of thousands of years. Pressure builds up in colossal magma reservoirs several kilometers deep until it becomes strong enough to lift the rock above it by several meters. Rocks crack under the pressure until they finally give way and billions of tons of gas and ash blast out at supersonic speed. An insane explosion of at least 1,000 cubic kilometers that impacts every corner of the globe. And yet, that is only a small portion of the magma reservoir. Super eruptions are like a boiling pot of water popping its lid off and spitting a bit off the top. Afterwards, the ground collapses into the void left behind, forming a hole called a caldera. Under this caldera, pressure starts building again until the volcano gathers enough energy for another super eruption. But this could take hundreds of thousands of years. It's estimated that one of the few volcanoes capable of super eruptions on Earth could cause a catastrophic eruption every 17,000 years on average. That would make them far more frequent than comparable asteroid impacts. The most recent super eruption is the Oronui eruption 26,500 years ago in New Zealand. With the force of dozens of billions of tons of TNT, a Mount Everest-sized pile of explosives, a huge portion of the landscape was scooped out and thrown into the atmosphere. It left behind a caldera spanning 20 kilometers, and it caused the entire southern hemisphere to undergo a period of abrupt cooling. Though among super eruptions, it's a mere firework. The Lake Toba eruption of 74,000 years ago was a much more significant turning point in history. It released a gargantuan 5,300 cubic kilometers of material, enough to blanket parts of South Asia, in 15 centimeters of ash and trigger a rapid 4 degrees Celsius drop in global temperatures. It's possible that the volcanic winter lasted 10 years, followed by worldwide droughts for centuries. Earth's climate might have not recovered for 1,000 years. The largest volcanic events we know of were not really huge explosions, but floods of millions of cubic kilometers of lava. The grand finale were the Siberian traps around 250 million years ago, a continuous release of lava for 2 million years. They raised the ocean temperatures to over 40 degrees Celsius, which caused the Permian-Triassic extinction, killing over 90% of all species. Earth's surface needed 9 million years to recover. These sorts of eruptions don't change the climate, they are the climate. But thankfully, we haven't seen anything even remotely close to that scale in many millions of years. So, should you be scared of supervolcanoes? Definitely not. They've been used to frighten many people and are overhyped as an unavoidable apocalypse. The most famous one, Yellowstone, will erupt again, but they will be relatively small eruptions. Natural disasters for sure, but not enough to devastate the US or come close to ending humanity. The chance of a VEI-8 eruption in the next few hundred years is less than 2%, and more importantly, it wouldn't come as a sudden surprise. However, less powerful but more frequent eruptions can also do serious damage to our civilizations and are in many ways a much greater concern. So we must watch for slow changes in magma reservoirs like ground swelling and temperature increases to get an early warning that can save the lives of people living the closest to a volcano. And there's time to develop solutions that can remove sulfur and ash from the stratosphere to eliminate the root cause of the climate disruption we've seen from previous eruptions. Who knows, maybe we'll even be able to turn this force of destruction into an agent for good by exploiting the geothermal energy held in their giant magma reservoirs. We've done this work for so many other disasters, and we are already doing things we could only have dreamed about decades ago, like sending a probe to perform our first asteroid redirection test. With determination, humanity really can solve anything. So while deep below us an angry hell is churning, and waiting for its moment, you can sleep well tonight. Casually watching a video on YouTube on a computer more powerful than anything humanity could build a few decades ago. This progress and all the wonderful machines you take for granted are built on a few rare and precious materials with names like terbium, neodymium, or tantalum. Getting these rare materials from the ground into your devices is ugly. The mining industry is responsible for air and water pollution and the destruction of entire landscapes. Dangerous chemicals like cyanide, sulfuric acid, or chlorine are used to extract the resources, harming biodiversity, workers, and locals. And rare resources are also political tools when countries restrict access to them to get their way. But what if we could replace the mining industry on Earth with a clean process that can't harm anyone? Well, we can. All we need to do is look up. Asteroids are millions of trillions of tons of rocks, metals, and ice, leftovers from the cloud that became the planet 4.5 billion years ago. They can be as small as a meter or protoplanets the size of entire countries. Most of them are concentrated in the asteroid belt and the Kuiper belt, while hundreds of thousands more do their own thing between the planets. As space travel is becoming more feasible, scientists and economists have begun looking at the resources found in these asteroids. Even relatively small metallic asteroids may contain trillions worth of industrial and precious metals like platinum. And bigger asteroids like 16 Psyche could contain enough iron-nickel to cover the world's metal needs for millions of years. At current market prices, the rare raw materials alone would be worth quadrillions of dollars. Well, not really, but technically. For example, there are more than 20 million tons of gold in the ocean's water, worth roughly $750 trillion US, but filtering out the gold would be so expensive that you'd lose money selling it. Right now, asteroid mining has exactly this problem. It's too expensive to replace mining on Earth. Billions of dollars worth of valuable resources in space are worthless if it costs trillions to get them. What makes it so hard? The principles behind mining an asteroid are simple. The basic idea is to choose an asteroid, move it to a place where it's easy to process, and then take it apart to turn into useful products. Unfortunately, all of this collides with fundamental problems humans have yet to solve. Going to space is expensive. It costs thousands of dollars in rocket fuel for each kilogram just to reach a low Earth orbit. Going further out into deep space costs thousands more. We need cheaper space travel to make asteroid mining profitable. One solution is to switch from classical rockets to electric spaceships. We already use electrical rocket engines for many of the space probes on science missions. In principle, we only need to build bigger ones. While electrical engines are not powerful enough to fly to space, they require only a tiny amount of fuel to go very far once they're in space. This means we don't need to spend a lot of money on fuel only to transport fuel into space. This doesn't solve the whole cost problem, but it makes it easier to start our first mission. Now that we have an electric asteroid mining spaceship, we need to find the right asteroid and get it there. We've already successfully visited asteroids with space probes and even collected samples. Still, to make it easier and cheaper, our first targets will probably be near-Earth asteroids. Asteroids that orbit, well, near Earth. After a few months of travel, our spaceship finally arrives at our asteroid. Weirdly formed, littered with small impact craters, it hasn't changed much for billions of years. The first thing that needs to be done is to secure the asteroid and stop it from spinning. There are multiple ways to do this, like vaporizing material with a laser or stopping the rotation with thrusters. Once we have a stable asteroid, we need to wait. Orbital mechanics are complicated, but if you push something in the right direction at exactly the right moment, you can move very big things with very little force. So we wait for exactly the right moment. Our ship fires its thrusters and nudges the asteroid into a trajectory that takes it near our moon. The moon is useful because we can borrow its gravitational pull to put the asteroid in a stable orbit around Earth, which saves even more fuel. Again, the trip takes months. But all the time since our ship was launched has not been wasted. The first space mining and processing equipment has been installed in orbit and is now carefully moving towards the asteroid. The processor works very differently than on Earth. Giant mirrors focus sunlight and heat up asteroid rock to boil out the gases. Grinders break up the dried rocks into gravel and dust, and centrifuges separate dense from light elements. Even if we only extract 0.01% of the asteroid's mass in precious metals, this is still several times more than you'd get from the same amount of ore on the ground. But what now? How do we get our precious metals safely back to ground? There are a few ways, like loading it into reusable rockets that return to Earth from space. Or if our processor contains 3D printers, we can print a faster and cheaper delivery system. Heat-shielded capsules filled with gas bubbles. These can just be dropped into the oceans where ships tow them away. This could be the starting point of humanity's first real steps towards colonizing the solar system. As our infrastructure and experience grows, our missions get more and more sophisticated. Parts and fuel produced on asteroids don't have to be launched from Earth at all. The first mining operation makes the second one easier, and so on. While the space industry grows and precious materials become cheaper, eventually we could stop mining on Earth. Even the idea of toxic mining down here might become something weird and anachronistic, like having an open fire in your living room. Landscapes ravaged by pollution will heal, while the technological wonders we're used to get cheaper and less toxic to make. None of this is science fiction. We don't need fancy materials or new physics to make asteroid mining happen. We could start building this future today. All we need is an initial push. Sometimes the world feels, boring. We've visited all the remote islands, conquered the Arctic, and penetrated the deepest jungles. But there is still one place to explore. It's a wet and deadly desert inhabited by mysterious creatures living in total darkness. The deep sea. Let's dive down. When we look at the sheer scale of the Earth's oceans, it's hard to believe that less than 2% of all biomass on Earth lives here. And of that small percentage, around 90% is located close to the surface in the first 200 meters. This is where we begin our journey. Here, light can still penetrate the water, which allows photosynthesis to occur. Phytoplankton, trillions and trillions of single-celled algae and bacteria make up the foundation of the ocean's ecosystem, and they're consumed by bigger plankton who are consumed by other species. The seafloor at this depth is akin to the Amazon rainforest and is often covered with coral reefs, algae and other sea plants that are home to a plethora of sea animals. So far, we've focused most of our attention on this comparatively pleasant environment where we fish, swim, pollute, and do science. So, let's dive deeper. Moving from familiar coastal waters into deeper, more remote waters, we eventually reach the edge of the continental shelf, where we're confronted with the continental slope, the long descent down to the deep sea. With every additional meter of water, light fades drastically, which means there are basically no more plants, and the seemingly steep continental slope begins to remind us of the surface of the moon. Looking out, we're faced by what seems to be endless open water. Let's leave the slope behind us and enter what's known as the Twilight Zone, the portal to the deep sea. As we sink down further, the water pressure rises to deadly levels. The deepest scuba dive ever came in at 332 meters. At that depth, the pressure is like having 200 cars stacked on top of you. Yet we've only completed 3% of our journey. While this region seems pretty grim, many fish and other animals actually spend at least half their lives down here. During the day, it's a good place to rest and recover, hidden from predators in the vast, dark waters. At night, they can travel more safely into shallower zones to feed in the food-rich surface waters. In this transition zone between twilight and darkness, light becomes a powerful tool. Over 90% of the species indigenous to this deep environment use bioluminescence chemicals to create light. They do so as camouflage against the very faint sunlight, to send signals to potential mates, or to confuse and scare attackers. Or they use light to hunt. Another tool for survival in the dark is teamwork. At around 700 meters, we encounter a colony of siphonophores. They can be up to 50 meters in length, but are only as wide as a broomstick. To attract prey, a colony creates a tragically beautiful bright blue or red light and deploys a curtain of tentacles filled with toxic needles that kill anything that comes too close. But most species living down here have to rely on an unlikely resource: marine snow. White, flaky stuff that constantly sinks from the surface to the bottom of the ocean. It consists of dead plant or animal parts, fecal matter, shells, sand, or dust. Even though this doesn't sound very tasty, without this crucial resource, life in the deep sea would starve. It's in this area that the most fascinating battles between two unlikely enemies could happen. Sperm whales hunt and attack giant squid the size of a house. While the squid fight back ferociously, they probably don't stand a chance, but they do leave permanent marks on their killer's skin. As we reach 1,000 meters, deeper than the tallest structure built by humans, we need to be careful. This is the Midnight Zone, a place of utter darkness. A barely explored wet wasteland consisting of nothing but endless black open water. At these depths, it's harder for a human to take a swim than to take a walk in space. Finding food down here is really hard, so life had to adapt and become extremely energy efficient. Like the 30-centimeter long vampire squid that floats through the water without motion, with long and slender catching arms extended. They're covered in tiny stiff hairs which brush food from the water. This saves a lot of energy compared to actively catching food. For carnivorous fish, it's much harder to find food since living prey is quite rare down here. So the hunters have to get a perfect grip on their victim on first strike, otherwise it will escape into the dark. Many deep-sea predators have several sets of long and deadly teeth. Like the viperfish, which uses its long fangs to trap even large prey and swallow it whole. Or the frilled shark with its impressive set of 300 teeth, which are curved backwards to hook their victims in their mouths. We sink further, below the 3,800 mark, as deep as the grave of the Titanic. We are now at abyssal depths. Here, life happens in slow motion. Preserving every last bit of energy is crucial for survival. Everything down here hovers motionless or swims in a slow, elegant fashion. The only time the animals living in this zone move fast is when they have to escape danger. Like the Dumbo octopod paddling with its ear-like fins, or the grenadier's fish with its slow, eel-like tail beats. At 4,000 meters, we finally reach ground again, the abyssal plain. It's covered in grey mud and rocks, dusted with the remains of marine snow, which is consumed by animals like sea cucumbers, shrimp, sea urchins, and sea worms. In some regions of the seafloor, small dark mineral deposits can be seen. These are manganese nodules. Deep-sea corals and sponges use them to anchor themselves on the bottom of the sea. Though life is sparse on the deep seafloor, even down here there are oases. In the rift valleys, where tectonic plates are splitting apart, magma heats up seawater and creates dark jets of water and minerals as hot as 400 degrees Celsius that form elaborate chimneys and towers. Extremophile bacteria use the minerals to create organic substances that are the basis for unique ecosystems. As we descend further, we reach the deepest point of the abyssal plain at 6,000 meters. For most of the seafloor, this is as deep as it gets. But if we want to get to the deepest point of the oceans, we're actually only halfway there. Let's enter the Hadal Zone, the underworld of the sea. It consists of long, narrow trenches that only make up around 0.25% of the oceans and are among the most extreme environments on Earth. Only extremophiles exist down here, like the ethereal snailfish that holds the record for the deepest living fish ever seen at around 8,000 meters. We see spiky and sharp black rocks rush by as we sink down to more than 10,000. Until we reach the final slope, a trench inside the larger Mariana Trench with gently sloping sides that enframe a valley about 1.6 kilometers wide. This is it. The deepest point, the Challenger Deep, 11,000 meters below the surface. The water pressure here is 1,086 bar. Taking a swim here is like having to balance 1,800 elephants on top of you. But even here, life has found a way to thrive. Next to sea cucumbers, white and light pink amphipods wiggle their way through the water. Their size is astounding. While their shallow water cousins are merely a few centimeters long, the deep-sea version can reach up to 30 centimeters. And there are other things floating elegantly through the water. Plastic bags that were found by scientists in 2018. Even the remotest place on Earth is not safe from human influence. There's nothing left to do now, and our oxygen is running out, so we begin our ascent. After hours of traveling through dark nothingness, we finally see a glimpse of light. We arrive back at a calm surface. The oceans are so deep. There is so much of them. We owe it to ourselves and to our descendants to preserve them as well as we can. There are still so many wondrous things left to be discovered. Climate change is just too much. There's never any good news. Only graphs that get more and more red and angry. Almost every year breaks some horrible record, from the harshest heat waves to the most rapid glacier melt. It's endless and relentless. We've known for decades that rapid climate change is being caused by the release of greenhouse gases. But instead of reducing them, in 2019 the world was emitting 50% more CO2 than in the year 2000. And emissions are still rising. Why is that? Why is it so hard to just stop emitting these gases? Our collective CO2 emissions can be expressed as a product of 4 factors and their relationship with each other. 2 of them explain why worldwide CO2 emissions are still rising, and 2 explain how we can stop that. Population size, economic growth, energy intensity, and emissions per energy unit produced. Number 1. Population size. People need food, homes, and clothing, and they demand luxury products from iPhones to $1 cheeseburgers. More people, higher CO2 emissions. It's a very simple equation. The global population is growing, and according to the UN, it will level off at about 11 billion in 2100, which is 40% more than today. The only way to slow down this growth is investment in healthcare and access to contraception and education in developing countries. But even with massive investment, it will take a few decades for the effects of lower birth rates to manifest themselves. So the global population will keep growing for the foreseeable future, and as a consequence, global CO2 emissions will rise over the next few decades. Number 2, growth or getting richer. But it's not just about our numbers. The richer and more developed we are, the more emissions our lifestyle produces. A programmer in the US has a higher CO2 footprint than 50 farmers in Uganda. The world's wealth is growing almost everywhere. And although it's far from evenly distributed, economic growth has led to the highest standards of living and the largest reduction in extreme poverty in human history. Growth has become the dominant mantra of the world's economies, no matter what kind of political system they have. It's unlikely that rich countries will give up the concept of growth anytime soon. But even if they were to, developing countries want to become rich too. For billions of people, the end of growth would probably mean staying poor, and so developing countries are not willing to stop growing their economies. All in all, we can be sure that growth as a guiding economic ideology is not going to go away anytime soon. More countries and their citizens around the world will grow and become richer, while the rich economies will continue to grow their wealth. There are some signs that growth can be decoupled from CO2 emissions, but we're not close to that yet. As a consequence of this growth, CO2 emissions will rise. Okay, so far we've learned that because of population growth and economic growth, humanity's CO2 emissions will increase. which is the opposite of what should be happening. We need to slow, peak, and then reduce annual emissions. The next two factors describe how we can actually do this. Number 3. Energy intensity. Energy intensity describes how efficiently we use energy. A street food vendor in rural Brazil might burn coal to cook, while a street food vendor in France might use an induction stove powered by nuclear energy. The latter is way more efficient. The more efficient something is, the less energy we need to do something, be it powering a metropolitan area or grilling a kebab. So making our technology more efficient and coming up with more efficient ways to organize our societies is one of the most important ways to reduce the modern world's CO2 dependency. This can mean everything from reducing power consumption with AI, the electrification of the transportation and industrial sectors, or sustainable concrete production. The opportunities for improvement are almost limitless, and human ingenuity can run wild. But we know that increasing efficiency alone will not be enough, mostly for 3 reasons. 1. Direct rebound effects. This means that once something becomes more efficient, it's used more, and so overall the increased efficiency does not lead to a reduction as impressive as you would first think. Or worse, sometimes more efficiency makes humans not use less of a resource, but more of it. When planes became more fuel efficient, ticket prices decreased and more people started to travel by plane. So making things more efficient does not automatically mean less energy use in total. It might have the opposite effect. 2. Indirect rebound effects. Sometimes when you save money on a thing that's become more efficient, you might spend it elsewhere. For example, if you buy a more fuel-efficient car, you save money on fuel and end up with extra funds in your bank account that you might spend on a vacation and take a flight with. So, in the end, you might actually emit more CO2 despite getting a more efficient car. 3. And lastly, the more you optimize for efficiency, the harder and more expensive it becomes to get more efficient. So over time, the return on investment slows down. And with many technologies, we are already pretty efficient. But regardless of how efficient we make our economies, as long as we need at least some energy, we will have emissions. Efficiency alone won't create a zero-carbon world. This brings us to our last factor. Number 4. CO2 emissions per energy unit used, or our global carbon footprint. Humanity's global carbon footprint is the CO2 released per energy unit generated. For example, coal plants release much more CO2 than solar power per unit of energy. This relationship is crystal clear. The more fossil fuels we burn, the higher our CO2 output. Fossil fuels are the greatest lever humanity has right now. Of course, it's impossible to shut down coal and oil overnight without throwing society into chaos. But the reality is that we're not doing nearly enough to keep fossil fuels in the ground and use lower carbon alternatives. We need to do 2 things to speed the transition away from fossil fuels. First, we need to use the real leverage we have today with today's technology. There are a lot of things we can do extremely quickly. We can leave nuclear power plants online longer. We can cut subsidies to the fossil fuel industry and funnel them into renewables. We can price carbon emissions harshly and increase the price each year to create strong incentives for the world's industries to transition. We can enforce strict standards for energy efficiency and for any type of new construction. We can phase out fossil fuel vehicles. Next, we also need to invent new and better technology. Without new technologies and innovation, it will be impossible to achieve a zero CO2 emission world, be it from technologies like carbon capture or a new generation of nuclear power plants to new batteries that revolutionize the energy storage from renewables. But innovation takes time, years and decades, and we don't have this time. Every year we keep adding more carbon to the atmosphere. This means we can't keep relying on innovation alone. We need to find ways to reduce emissions today while we invent what we will need in the future. The less fossil fuel we burn over the next few years, the more time we give innovation to catch up. The more low-carbon energy infrastructure we build today, the more we can compensate for economic growth and the people born today. The more coal power plants in construction we stop from being finished, the more CO2 we save. Neither innovation nor the alternatives we're using today alone can solve rapid climate change. But innovation, together with a decisive move away from fossil fuels where it's possible today, could do it. Solving climate change will be complicated. We have to account for the needs of billions of people and the reality that right now, society runs mostly on fossil fuels. This will not change overnight, but it needs to change as quickly as possible. And it is still very much possible. What would happen if you were to bring a tiny piece of the sun to Earth? Short answer, you'd die. Long answer, it depends which piece of the sun. Like most of the matter in the universe, our sun is neither solid, liquid, or gas, but plasma. Plasma is when stuff is so hot that the nuclei and electrons can separate and flow around freely, which creates a goo-like substance. So you can imagine our sun as an extremely big, spherical ocean of very hot goo. The deeper you go, the denser and weirder the goo becomes. So let's bring 3 samples, each the size of a house, to our lab here on Earth and see what happens. First sample, the chromosphere. The chromosphere is the atmosphere of the sun, a layer of sparse gas up to 5,000 kilometers deep that's covered in a forest of plasma spikes that can be almost as big as Earth. It's pretty hot here, between 6,000 and 20,000 degrees Celsius, but if we brought a sample of it to Earth, we're not really getting our money's worth. In the area where we take our sample, the chromosphere is over 1 million times less dense than air, so compared to our atmosphere at sea level, it's basically the same as bringing the vacuum of space down to Earth. The moment our sample arrives, it would immediately be crushed by Earth's atmospheric pressure and implode. Air would rush to fill the vacuum and use as much energy as 12 kilograms of TNT in the process. This creates a high-pressure shock wave which shatters glass, ruptures eardrums, and maybe some internal organs. If you're standing too close, it could kill you, so you'd better keep your distance. Let's go deeper. Second sample, the photosphere. Beneath the chromosphere is the glowing surface of the sun, the photosphere, which produces the light we see. It's covered in a grid of 1 million hotspots called granules, each of them about as big as the United States and over 5,000 degrees Celsius. These granules are the tops of convective columns, churning gas that brings the heat up from the center of the sun to its surface. In these columns, a few hundred kilometers down, we take our second plasma sample. It has about the same pressure as our atmosphere on Earth. Though still much less dense than air, its heat supports it, so it won't implode. Our sphere now carries twice as much energy, as much as 25 kilograms of TNT, but this time as heat. For a dazzling instant, this plasma would glow with 1 million times the brightness of the sun seen from Earth, instantly lighting fires throughout our lab. But a few milliseconds later, those fires are all that's left. The plasma has cooled to harmless gas, floating up from the flaming ruins. What if we go deeper? Third sample, the radiative zone. Here, the plasma is about 2 million degrees Celsius and so dense and tightly packed that it creates a sort of maze for itself. Energy in the form of photons tries to escape but has to wander for hundreds of thousands of years, bouncing endlessly from particle to particle until it eventually finds an exit. Bringing matter from here to our lab is what experts call a very bad idea. As soon as it arrives in our lab, the extreme pressure that holds the plasma tightly together is gone, and the material explodes with the power of a thermonuclear weapon. Our lab, as well as the city around it, will be destroyed in an instant. On the bright side, there won't be any radioactive fallout. With our lab destroyed, we can abandon the illusion that we're trying to do any science today. What if we go much, much deeper? Last sample, the core. Here in the central 1% of the star, we find a third of the sun's mass. The matter here is compressed by the weight of the entire star above it. In the center of the core, the temperature is 15 million degrees, hot enough to make helium by smashing together hydrogen, powering the sun by nuclear fusion. In billions of years after the death of the sun, this core will remain as a white dwarf. If we brought a sample of it to Earth, it would cause a lot of inconvenience. The biggest nuclear weapon ever detonated had an energy of 40 megatons of TNT, or a cube the size of the Empire State Building. Our sample has the equivalent of 4,000 megatons. This is 4 billion tons of TNT, or a cube 1.3 kilometers high. To give you a sense of scale, this is the cube inside Manhattan. Once the sphere arrives on Earth, this super dense matter expands instantly and creates an explosion with the force of, well, the sun. If we get the sample in Paris in the morning, the citizens of London would see what looks like a second sunrise, but one that gets brighter and brighter and hotter until London burns to ashes. In a radius of about 300 kilometers around the blast, everything would be burnt. The shock wave would travel around the Earth multiple times. Most buildings in Central Europe would be flattened, eardrums would rupture, and windows break across the continent. The explosion would be apocalyptic, possibly human civilization ending. If humans did survive, we could count on the dust blown into the atmosphere to create a small ice age. So, if there is one tiny bright side, it would be that the explosion might be an effective way to control human-caused climate change for a few decades. While this is definitely a good thing, all in all, we conclude that we should not try to bring the sun to Earth. What is hydraulic fracturing, or fracking? Since the Industrial Revolution, our energy consumption has risen unceasingly. The majority of this energy consumption is supplied by fossil fuels like coal or natural gas. Recently, there's been a lot of talk about a controversial method of extracting natural gas, hydraulic fracturing, or fracking. Put simply, fracking describes the recovery of natural gas from deep layers inside the Earth. In this method, porous rock is fractured by the use of water, sand, and chemicals in order to release the enclosed natural gas. The technique of fracking has been known since the 1940s. Nonetheless, only in the last 10 years has there been quite a fracking boom, especially in the USA. This is because most conventional natural gas sources in America and on the European continent have been exhausted. Thus, prices for natural gas and other fuels are rising steadily. Significantly more complicated and expensive methods, like fracking, have now become attractive and profitable. In the meantime, fracking has already been used more than 1 million times in the USA alone. Over 60% of all new oil and gas wells are drilled by using fracking. Now, let's take a look at how fracking actually works. First, a shaft is drilled several hundred meters into the Earth. From there, a horizontal hole is drilled into the gas-bearing layer of rock. Next, the fracking fluid is pumped into the ground using high-performance pumps. On average, the fluid consists of 8 million liters of water, which amounts to about the daily consumption of 65,000 people, plus several thousand tons of sand and about 200,000 liters of chemicals. The mixture penetrates into the rock layer and produces innumerable tiny cracks. The sand prevents the cracks from closing again. The chemicals perform various tasks. Among other things, they compress the water, kill off bacteria, or dissolve minerals. Next, the majority of the fracking fluid is pumped out again. And now the natural gas can be recovered. As soon as the gas source is exhausted, the drill hole is sealed. As a rule, the fracking fluid is pumped back into deep underground layers and sealed in there. However, fracking is also associated with several considerable risks. The primary risk consists in the contamination of drinking water sources. Fracking not only consumes large quantities of fresh water, but in addition the water is subsequently contaminated and is highly toxic. The contamination is so severe that the water cannot even be cleaned in a treatment plant. Even though the danger is known and theoretically could be managed, in the USA already, sources have been contaminated due to negligence. No one yet knows how the enclosed water will behave in the future, since there have not yet been any long-term studies on the subject. The chemicals used in fracking vary from the hazardous to the extremely toxic and carcinogenic, such as benzol or formic acid. The companies using fracking say nothing about the precise composition of the chemical mixture. But it is known that there are about 700 different chemical agents which can be used in the process. Another risk is the release of greenhouse gases. The natural gas recovered by fracking consists largely of methane, a greenhouse gas which is 25 times more potent than carbon dioxide. Natural gas is less harmful than coal when burned. But nonetheless, the negative effects of fracking on the climate balance are overall greater. Firstly, the fracking process requires a very large consumption of energy. Secondly, the drill holes are quickly exhausted, and it's necessary to drill fracking holes much more frequently than for classical natural gas wells. In addition, about 3% of the recovered gas is lost in the extraction and escapes into the atmosphere. So how is fracking and its expected benefits to be assessed when the advantages are balanced against the disadvantages? When properly employed, this technique offers one way in the short to medium term to meet our demand for lower-cost energy. But the long-term consequences of fracking are unforeseeable, and the risk to our drinking water thus should not be underestimated. Our first ever PC game, Starbirds, is out now in early access. Find out more at the end of this video. Imagine, a stadium-sized asteroid is going to hit Earth in 2 weeks. Even at this moderate size, a fireball brighter than the sun tears through the atmosphere at 60 times the speed of sound, and the destructive power of 4,000 Hiroshima bombs flattens cities, killing millions. This isn't science fiction. Many killer asteroids were only spotted at the last moment. In 2019, asteroid OK, as big as a 30-story building, was discovered just 1 day before it grazed Earth closer than some of our satellites. Last year, the even larger asteroid MK was spotted 13 days before it passed us closer than the Moon. If they'd have hit Earth, they would have unleashed the destructive power of 3,000 and 9,000 Hiroshima bombs. Stunningly enough, humanity doesn't really have a plan for this. Scientists have devised all kinds of tricks to push dangerous asteroids away, painting it so sunlight will deflect it, landing thrusters to steer it, scorching it with lasers, or even crashing spacecraft into it. But they all have a big problem. They're the equivalent of trying to deflect a cargo ship by throwing a bag of potatoes at it. They do move the asteroid, but only by a tiny bit. With these methods, you need to act years or even decades in advance to make an asteroid miss the Earth. But very recently, scientists have developed a new, spectacular way to destroy killer asteroids that we could implement with today's technology. Let's see how this works with our 100-meter asteroid heading for Earth. The secret weakness of asteroids. For a long time, people imagined asteroids as being gigantic stones made of rock and metal. But it turns out most of them aren't like that. They're more like bags of loosely packed gravel, heaps of pebbles, precious minerals and dust barely held together, which means that instead of just nudging them, we can do something better, pulverize them. And the obvious choice is, of course, a nuke. So let's go. We load up a nuclear warhead, launch, aim at our deadly asteroid and... Oh, the asteroid destroyed the nuke. Asteroids can approach Earth at 70,000 kilometers an hour, enough to cross the Atlantic in 5 minutes. No bomb we've ever made could survive such an impact. So if we go for a head-on collision, the asteroid will wreck the nuke before it even has a chance to explode. Okay, easy. Let's explode the bomb before it touches the asteroid. Scientists have estimated the optimal distance, which for our 100-meter killer friend would be a few tens of meters above the surface. Launch, set the timer, and... The explosion has made a dramatic crater and nothing else. Unfortunately, in space there's no air to carry a shockwave, so most of the explosion's energy is lost. The rock will still hit us in 2 weeks, only a few kilometers to the left. Striking such a behemoth with a nuke is like hitting our cargo ship with a washing machine instead of potatoes. Better, but still useless. Okay, let's go the movie route. Land someone on the asteroid, drill a hole, and bury a nuke inside to avoid all of these problems. And indeed, this is possible in theory, albeit suicidal in practice. Landing on any space body is a nightmare. Even on fairly big Mars, whose surface we know almost perfectly, roughly 70% of our attempts have failed. So imagine the chances of landing a crew and a nuclear bomb on a small and extremely fast asteroid discovered just 2 weeks in advance. Even if we succeeded, drilling in microgravity is painfully slow since there's no downward pull to help you. So we'd need an agonizing amount of time that we don't have. So sadly, that's not the answer. We have to think less like Hollywood and more like a lumberjack. The smart way. If you want to split a log, you don't hit it with a rock. You use an axe, a dense and perfectly shaped tool designed to break things apart. And just in the same way, scientists have found a new tool to destroy asteroids: super dense, ultra-fast cosmic bullets. We won't even have to shoot them. Our cosmic bullets are called penetrators. A few meters long, slim and made of tungsten, a metal way denser and harder than rock. They work in an extremely simple way. You just put the penetrators in the way of the asteroid to float silently in space. From the perspective of the asteroid, you wouldn't see a few tiny bullets sitting still. You'd see them rushing at you at 70,000 kilometers an hour. It doesn't matter who stands still and who's fast. But this speed means that by far the longest part of this mission is to get to the asteroid in time. We can't destroy it too close to Earth because its fragments will slam into the atmosphere all at once with the power of thousands of nuclear bombs. Our atmosphere can absorb isolated chunks, but if thousands of them strike together, their shock waves will add up and kill millions. So instead, we need to get it 1 day before impact, when the asteroid will be nearly 2 million kilometers away, more than 4 times further than the Moon. A vast distance, but doable. Our current rockets can cover this in about a week. We'll just send one penetrator about 2 meters long and weighing 2.5 tons. Once our rocket arrives, it puts the penetrator in place to cause maximum damage, and then we wait. A tiny speck of light appears in the vast distance, and then suddenly it's here, shooting at us faster than the speed of sound. We'll slow down time to see exactly what happens. The asteroid crashes into the penetrator so fast and with so much violence that the power of 120 metric tons of TNT is released into the asteroid. The rock vaporizes and the tungsten melts away, carving a wound that tunnels through the asteroid. The damage is too much, and with all of this energy looking for a place to go, the asteroid is blasted into thousands of pieces. The debris spreads out into a diffuse cloud. A day later, the fragments hit Earth, dispersed over hundreds of thousands of square kilometers and turning an apocalypse into a mostly harmless show of cosmic fireworks. So if we prepare and get everything ready, spotting a killer asteroid with 2 weeks' notice would be enough. But this was just a small asteroid. What if we face a cosmic mountain, a planet killer carrying the destructive power of tens of thousands of nuclear arsenals? The non-avian dinosaurs would tell you about it, but they're dead. What if it is a planet killer? Planet killers are objects so vast and powerful that they would end most life on Earth in a single strike. The most dangerous ones are comets from the outer fringes of the solar system, so distant and dark that tracking them is impossible. Comets are dirty ice balls the size of mountains, more fragile than pure rock, but also much faster and violent, traveling at around 140,000 kilometers per hour. In 2020, the comet Neowise, with the power of 6,000 times all the nuclear bombs on Earth, was discovered just 4 months before its closest approach to Earth. What if we find such a beast 6 months before it's going to crash into us? Do we have a chance of surviving this? Unfortunately, this would be extremely hard for a bunch of reasons. First of all, our planet killer comet has so much more mass than a tiny killer asteroid that simply breaking it into millions of pieces would not help us that much. The chunks that hit Earth would still be massive and numerous enough to set the sky ablaze and kill most life on Earth. So we need to make most, if not all of its fragments completely miss Earth. But to do that, we need to destroy it much further away, as far away as Mars. And to destroy a mountain, we need way more penetrators. Hundreds of thousands. And this is, well, a huge problem. To travel this far and to transport this much payload, we need at least 24,000 super heavy rockets. As of today, humanity has 2, and they're not really finished yet. Even if all the industries in the world do nothing but switch to building rockets, we wouldn't finish in time. if we actually discovered a planet killer today, there's literally nothing we could do about it. Except maybe if we combine penetrators with a bit of Hollywood and our old friend the nuclear bomb, there is still a way. For this plan to work, we basically need to have all the parts ready beforehand. A rocket like NASA's SLS, the one planned to take astronauts to the moon, loaded up with everything we need, ready to launch. As soon as the planet killer is spotted on its way to wipe us out, we launch a single rocket to meet it. For 5 long months, it travels through the nothingness of space as life on Earth nervously continues. Finally, it reaches its destination a bit beyond the orbit of Mars. Now, we deploy 5 massive penetrators in sequence, one perfectly lined up 2 kilometers after the other. The engineering challenge of aligning and timing this correctly is horrendous, and we only have one attempt. So, a few very brave astronauts go on this one-way trip to supervise the process with no way home. Nervous hours pass as all of humanity watches the skies and screens. And then the moment comes. The icy mountain of death appears in full, and then it's already here. Slow down time again. The comet smashes into the first penetrator at 140,000 kilometers an hour, unleashing the power of 2,000 tons of TNT. Ice, rock, and tungsten liquefy in an instant as the energy of the impact eats itself dozens of meters deep into the mountain. Here's the second one, perfectly hitting the same spot, punching directly into the crater, smashing, melting, drilling. The third and fourth penetrators repeat the process again, now smashing a tunnel about 100 meters deep. But this time, this is just a scratch on the surface of the monster. The comet is not really damaged yet. And then comes the final penetrator and its toxic load. 300 megatons in nuclear warheads, 20,000 times more energy than the bomb that destroyed Hiroshima. It travels deep into the tunnel, and just before it hits the end, it explodes. This time, the nuke works. Instead of hitting nothing in the vacuum, the energy of the explosion smashes into rock and gravel and ice. On top of vaporizing it from the inside, there's so much shock and push and punch that a frozen world billions of years old dies from within, turning into a cloud of millions of fragments spreading in all directions. Humanity is saved. To make this happen in reality would take unprecedented planning and precision, and yet it's possible. Not in a century with sci-fi technology, just with the rockets, engineering, and knowledge we already have today. Do we need nuclear energy to stop climate change? More and more voices from science, environmental activists, and the press have been saying so in recent years. But this comes as a shock to those who are fighting against nuclear energy and the problems that come with it. So, who's right? Well, it's complicated. To slow rapid climate change, the world needs to reduce greenhouse gas emissions to net zero. In 2018, 3/4 of global emissions were released through energy production, namely by burning fossil fuels. Energy is a broad term that describes all sorts of stuff, from moving things and people around to putting things big and small together or heating our homes. Currently, 84% of the world's primary energy comes from fossil fuels, 33% from oil, 27% from coal, and 24% from gas. Around 10% of the global oil supply is just used to burn in boilers to make our homes cozy and warm. Only about 16% of global energy is from low-emission sources, almost 7% from hydroelectric, 5% from solar, wind, bioenergy, wave, tidal, and geothermal combined, and about 4% from nuclear. So we pretty much rely on coal, oil, and gas to keep our civilization going, which means it's actually very hard to transition away from them. To have a chance of escaping fossil fuels without throwing humanity back into the Stone Age, one of the most impactful things we can do is to electrify as many sectors as possible. Electricity is the stuff that appears like magic when you plug something into a socket so you can watch YouTube. Every industry that can switch from burning fossil fuels to electricity needs to do so, from electric cars to electric heaters. Why do we need to bet so hard on electricity? Because we can produce electricity with low-emission technologies like solar, wind, or nuclear. So electricity is a real lever for a radical transition. But there are a few problems making this transition really hard. First of all, in most places in the world, electricity is still generated mostly by burning fossil fuels. And not only that, in the last 20 years, the world's electricity usage increased 73% in absolute terms. While we are installing renewables at record speeds, at the same time, the amount of fossil fuel we're burning for electricity still keeps rising year by year. Renewables have so far not been able to catch up with the demand for new electricity, and so despite our progress, emissions from electricity are still rising worldwide. The other alternative to fossil fuels is nuclear, and even though it's not renewable, its greenhouse gas emissions are tiny compared to burning stuff. But in the last 20 years, nuclear has basically stagnated. Countries like China, India and South Korea built new reactors, while Germany and Japan have been actively taking their nuclear plants offline. Which seems a bit weird if we look at the countries with the most low-carbon electricity in the world that get most of their juice mainly from two sources, nuclear or hydropower. Take France and Sweden. In France, only around 10% comes from fossil fuels, while 67% comes from nuclear and 23% from renewables, primarily hydro. In Sweden, almost 30% comes from nuclear power and about 45% from hydro. So we know that nuclear energy can work at scale. On the technical side, because of the lack of investment and innovation in the last few decades, the majority of the world's nuclear reactors are pretty old technology that's very costly to replace. In most Western countries, building nuclear reactors has become very expensive for a variety of reasons, like a loss of know-how in constructing them, policy changes, and increased regulatory constraints, so it can take a decade or longer just to finish a power plant. In contrast, countries like South Korea, China, India and Russia are able to build new nuclear reactors comparatively quickly and at a competitive cost. Still, generally in the West, the current generation of nuclear power plants are more expensive to build and maintain than most fossil fuel alternatives. There are also the concerns about nuclear waste and the fear of accidents, but we cover those in other videos in more detail. We have designs for nuclear reactors that solve many of their problems, namely small reactors that take less time and money to get started. There are also next-generation technologies that can already turn radioactive waste into new fuel, but so far these have not been deployed at a scale where they can have a significant impact on the nuclear sector. Considering these uncertainties, some argue that nuclear power is a dangerous relic of the past and that we should just let it go and focus on renewables. But while renewables undoubtedly are the future of electricity, they still have their own huge challenges to overcome before they can take over the vast majority of the electricity grid. The main problem is reliability and consistency. It's not always windy, and the sun doesn't always shine, especially in the mornings and evenings when humans need the most electricity. The variations between seasons don't make this issue easier. To make renewables reliable and not risk blackouts, we need massive storage capacities where we can save energy collected when the sun or wind are at their peak and release it later when we actually need it. Until this is possible, other sources of electricity need to provide a controllable load that creates the reliability of supply that our civilization needs to run properly. Eventually, we will be able to do this with renewables, but we need a lot of batteries or storage power plants. Right now, we simply don't have the tech and the capacities to make this transition fast enough to replace fossil fuels. But even if we could, there's another aspect we have to take into account. We're not just trying to kick fossil fuels out of electricity, we're trying to replace energy with electricity. If we're going to electrify sectors that currently use fossil fuels, like cars or heating, we will need significantly more electricity than we're currently using everywhere around the world. And if the electricity needs of the world population continue to grow as they have over the last 20 years, we'll need even more. It all comes down to one thing. No energy source is perfect. All have their own unique problems. Both renewables and nuclear energy require time, investment, and technological innovation. On their own, neither is ready to remove fossil fuels from our electricity grid, although activists on both sides claim that they are. In the end, the question is how we want to deal with all these challenges. Should we give up nuclear immediately and at least temporarily accept higher emissions? Will we try to extend the life of current nuclear reactors and shut them down afterwards while solving the shortcomings of renewables? Or will we invest in new nuclear technology to get new nuclear reactor types that are cheaper and safer? Or will we maybe do both? Opinion part starts here. Considering the risks that climate change poses for the biosphere and humanity, any technology that has a chance of contributing to a solution should be pursued. That's just good risk management and strategy. If preventing rapid climate change as quickly as possible is our goal, it might be a good idea to see nuclear and renewables not as opponents, but as partners. We know there's no time to waste, so we should keep all of our low-emission players on the field. As things are, both nuclear and renewables need innovation and investment. But if we don't know yet which technology will be ready how quickly, why not just invest in both and see what happens? And on the topic of current capacities, if we take nuclear energy offline right now, then that missing capacity will be replaced, at least partially, by fossil fuels. Even if new nuclear power plants in the West are expensive, in the long run it may be cheaper to build them as long as they prevent more fossil fuel capacity being added and paying for the consequences of rapid climate change. So, do we need nuclear energy? Well, it really depends how hard we choose to make things for ourselves. And in a world that's already having a really hard time quitting fossil fuels, why should we make things harder than necessary? When the gods granted King Midas one wish, he wished that everything he touched would turn to gold. Midas was delighted. Trees, rocks, buildings, all gold. But soon he found in horror that his food turned into gold as well. When he hugged his daughter to soothe his pain, he realized his mistake too late. The richest man in existence was starving, heartbroken, and alone. Humanity got a similar wish granted when we learned how to turn brown, stinky goo into magic. Plastic. Cheap, sterile, and convenient, it changed our lives. But this wonder of technology got a little out of hand. Plastic has saturated our environment. It has invaded the animals we eat, and now it's finding its way into our bodies. What is plastic? For most of our history, humans used stuff we found in nature to build the things we needed. But the invention of plastic roughly 100 years ago completely changed our world. Plastic is made from polymers, long, repeating chains of molecule groups. In nature, polymers exist everywhere. The walls of cells, silk, hair, insect carapaces, DNA. But it's also possible to create them. By breaking down crude oil into its components and rearranging them, we can form new synthetic polymers. Synthetic polymers have extraordinary traits. They are lightweight, durable, and can be molded into almost any shape. Not requiring time-consuming manual work, plastic can be easily mass-produced, and its raw materials are available in vast amounts and incredibly cheaply. And so the golden era of plastics began. Bakelite was used for mechanical parts, PVC for plumbing, electric gears and cases, acrylic as a shatter-resistant alternative to glass, and nylon for stockings and war equipment. Today, almost everything is at least partly made from plastic. Our clothes, phones, computers, furniture, appliances, houses and cars. Plastic has long ceased to be a revolutionary material. Instead, it became trash. Coffee cups, plastic bags, or stuff to wrap a banana. We don't think about this fact a lot. Plastic just appears and goes away. Unfortunately, it doesn't. Since synthetic polymers are so durable, plastic takes between 500 and 1,000 years to break down. But somehow, we collectively decided to use this super tough material for things meant to be thrown away. 40% of plastics are used for packaging. In the US, packaging makes up 1/3 of all the waste that is generated annually. Since its invention, we have produced about 8.3 billion metric tons of plastic, 335 million tons in 2016 alone. More than 6.3 billion metric tons of plastic have become waste since 1907. Piled up in one place, that makes a cube with a side length of 1.9 kilometers. So what did we do with all this waste? 9% was recycled, 12% burned, but 79% of it is sticking around still. A lot ends up in the ocean, around 8 million tons a year. That's so much plastic that it will outweigh all the fish in the ocean by 2050. Because it's everywhere, marine animals keep getting trapped in plastic and swallowing it. In 2015 already, 90% of seabirds had eaten plastic. Many animals starve with stomachs full of indigestible trash. In 2018, a dead sperm whale washed up in Spain. He had eaten 32 kilos of plastic bags, nets, and a drum. While this is tragic and makes for great magazine covers, there's an even more widespread, invisible form of plastic. Microplastics. Microplastics are pieces smaller than 5 millimeters. Some of them are used in cosmetics or toothpaste, but most result from floating waste that is constantly exposed to UV radiation and crumbles into smaller and smaller pieces. 51 trillion such particles float in the ocean, where they are even more easily swallowed by all kinds of marine life. This has raised concerns among scientists, especially about health risks from the chemicals that are added to plastic. BPA, for example, makes plastic bottles transparent, but there's also evidence that it interferes with our hormonal system. DEHP makes plastics more flexible, but may cause cancer. It would be pretty bad if microplastics are toxic because they travel up the food chain. Zooplankton eat microplastic. Small fish eat zooplankton. So do oysters, crabs, and predatory fish. And they all land on our plate. Microplastics have been found in honey, in sea salt, in beer, in tap water, and in the household dust around us. 8 out of 10 babies and nearly all adults have measurable amounts of phthalates, a common plastic additive, in their bodies, and 93% of people have BPA in their urine. There is little science about this so far, and right now it's inconclusive. We need a lot more research before panic is justified. But it is safe to say that a lot of stuff happened that we didn't plan for, and we have lost control over plastic to a certain extent, which is kind of scary. But just to make sure, we should simply ban plastics, right? Unfortunately, it's a bit more complicated than that. Plastic pollution is not the only environmental challenge we face. Some of the substitutes we'd use for plastic have a higher environmental impact in other ways. For example, according to a recent study by the Danish government, making a single-use plastic bag requires so little energy and produces far lower carbon dioxide emissions compared to a reusable cotton bag that you need to use your cotton bag 7,100 times before it would have a lower impact on the environment than the plastic bag. We're left with a complex process of trade-offs. Everything has an impact somehow, and it's hard to find the right balance between them. Plastic also helps solve problems that we don't have very good answers for at the moment. Globally, 1/3 of all food that's produced is never eaten and ends up rotting away on landfills, where it produces methane. And the best way of preventing food from spoiling and avoiding unnecessary waste is still plastic packaging. It's also important to note where the vast majority of the world's plastic pollution is coming from right now. 90% of all plastic waste entering the ocean through rivers comes from just 10 rivers in Asia and Africa. The Yangtze in China alone flushes 1.5 million tons of plastic into the ocean each year. Countries like China, India, Algeria, or Indonesia industrialized at an impressive pace in the last few decades, transforming the lives of billions of people. This development was so fast that the garbage disposal infrastructure couldn't keep up with collecting and recycling all the new waste this brought. If politicians in Europe and the US want to address this issue, investing in infrastructure in developing countries is just as important as fighting plastic pollution at home, with campaigns and redesigning products to minimize unnecessary plastic production. The bottom line is, As long as we don't address plastic pollution from a global perspective, we will not solve it. Plastic pollution is a complicated problem. We found a magic material and we had a really good time with it. But we need to be careful, or just like Midas, we'll end up in a world that we didn't wish for. The ocean conveyor belt and the Gulf Stream. Ocean currents have a direct influence on our lives. They determine our weather, our climate, and much more. The ocean currents and wind systems transport heat from the equator to the poles and operate like a large engine for the global climate. In the oceans, there are numerous currents. The so-called ocean conveyor belt is very important for our climate. This term describes a combination of currents that result in 4 of the 5 global oceans exchanging water with each other. They form a worldwide circulation system. The conveyor belt is also called the thermohaline circulation, with thermo referring to the temperature and haline to the salt content of the water. Both determine the density of the water. While the masses of water may be moved in part by wind, primarily the different densities of the global oceans are responsible for their movement. Warm water has a lower density and rises, while cold water sinks. The water's density also increases with a higher salt content. At the equator, the heat from the sun is especially strong, resulting in a lot of evaporation and thus a rise in the water's salt content. That is where the Gulf Stream begins. The Gulf Stream is very important for the European climate. Its length of 10,000 kilometers makes it one of the largest and fastest ocean currents on Earth, and it's very warm. At roughly 2 meters a second, it brings up to 100 million cubic meters of water per second towards Europe. A constantly blowing wind, the southeast trade wind, drives warm surface water to the northwest into the Gulf of Mexico, where it heats up to 30 degrees Celsius. The turning of the Earth and the west winds then direct the Gulf Stream towards Europe and split it up. One part flows south, another east to the Canary Current, and a third part flows north where it releases a lot of heat into the atmosphere as the North Atlantic Current. The water becomes colder there. Its salt content and density rise on account of evaporation, and it drops down between Greenland, Norway, and Iceland. There we also find the largest waterfall on Earth, the so-called chimneys, roughly 15-kilometer wide pillars with water falling up to 4,000 meters. 17 million cubic meters of water per second, or roughly 15 times more water than is carried by all the rivers in the world. This creates a strong maelstrom which constantly pulls in new water and is the reason that the Gulf Stream moves towards Europe. Countless species use the Gulf Stream as a means of transport on their trips from the Caribbean to northern areas. But it doesn't just bring us animals. An enormous quantity of warm air also comes with it. In order to produce the same heat which it brings to the shores of Europe, we would need 1 million nuclear power plants. That's why we also call the Gulf Stream a heat pump. Without it, the temperature would be significantly colder here, at least 5 to 10 degrees. Instead of lush fields, we would have long winters and sparse ice-covered landscapes in Europe. In the last few years, scientists and pundits in the media have repeatedly expressed the fear that the Gulf Stream could come to a standstill due to climate change. Because if the polar caps actually melt, the salt content in the water off Greenland would fall, as would its density. The North Atlantic Current would no longer be heavy enough, and so it wouldn't sink as usual. In the worst case, that would bring the Gulf Stream, our heat pump, to a stop. Some climate experts also assume that climate change could compensate for this effect. We know that it can be normal for the climate to change by looking at the development of the Earth over the last few million years. There are ice ages and warm periods. In the last ice age, a gigantic flood of melting water crippled the heat-bringing North Atlantic Current, covering the northern hemisphere in ice. Scientists have different views on the impact that climate change will have on the global ocean conveyor belt. But one thing is clear, when the climate changes, then the complex system of ocean currents and winds, which has remained fairly stable since the last ice age, will change in ways that we don't yet understand. We are prisoners on Earth. The universe taunts us by showing us all the places we can't ever visit. However, if our species wants to have a long-term future, we have to escape our prison. But what's keeping us here in the first place? Turns out we owe the universe a debt that is 4.5 billion years old. Everything with mass in the universe attracts every other thing with mass. We call this phenomenon gravity. The closer you are to a big chunk of mass, the stronger the attraction, or the more you're pulled in. This effect traps us on Earth. We can imagine this as being prisoners in a gravity prison or a gravity well. It's not a literal well, but a handy concept to understand how this works. Being in a gravity prison means that you owe gravity energy. But how can you owe energy? Because in our universe, things don't want to change their speed or direction. To convince them to move, you have to expend energy. Billions of years ago, the gravitational attraction of trillions of dust particles orbiting our Sun pulled them together until they formed a planet. This process used energy and created the gravity well we're now a part of. The deeper you are inside a gravity well, the more energy you owe gravity. If you don't find a way to get enough energy, you're not able to leave, no matter what you do. Because your atoms were once part of the dust that the universe expended energy on to get to this place. Okay, let's summarize all of that again. Objects in the universe don't like to move. You have to convince them to do so with energy. Gravity used energy to convince the parts that make up our planet to move together. This created a gravity prison in the process, trapping us. To escape it, we need to repay it with energy. Okay, how do we do that? To get into space, we need to go through a complicated process of exchanging energy. For this purpose, we build negative potential energy repaying machines, known by their more boring name, rockets. Rockets work by using some of the most energetic chemical reactions humans know about to basically explode fuel in a controlled way. This converts chemical energy into kinetic energy. The exhaust of the reaction is directed outwards and pushes the rocket away from Earth. By expending a lot of energy, we are increasing our gravitational potential energy, which is a complicated way to say that we're paying back our energy debt to gravity. But it's actually a lot trickier than that. When you burn fuel to get into orbit, you lose lots of energy to heat, the exhaust, and atmospheric drag, so you actually need much more. And you can't just pile a huge amount of really explosive, dangerous fuel close to your payload and detonate it. You need a controlled burn, which is complicated and makes your rocket very heavy, which means it has more mass. The more mass something has, the more energy you need to convince it to move. So you need more fuel to lift up your rocket. But if you need more fuel, that means you need more rocket to carry that fuel. But this makes your rocket heavier, thus requiring more fuel, which requires more rocket to carry that new fuel, and so on. At the end of this madness, you need closer to 100 times the weight of your payload to launch. Ariane 6, for example, the European rocket, will weigh 800 tons and should be able to transport 10 tons into geostationary transfer orbit or 20 tons into medium Earth orbit. But a rocket can only produce so much thrust, so there's a maximum weight after which it just won't take off. If you add too much weight, it won't lift off, so you can't just build bigger and bigger fuel tanks. This is the tyranny of the rocket equation, and it means spaceflight will never become easy. But wait, it gets worse. Getting to space is still not good enough. You're still inside the gravity prison at the edge of space and will crash back to Earth. Staying in space is much harder than getting there. To get to a stable position where it can stay for a while, a rocket has to reach low Earth orbit. To do this, you need a lot of kinetic energy, which means going extremely fast. At an altitude of about 100 kilometers, this is 8 kilometers per second, 28,000 kilometers per hour. Fast enough to travel around Earth in 90 minutes. Here, we can use a trick. Instead of flying straight up, we can go sideways. Earth is a sphere, so if you're going sideways fast enough, even though you're falling towards Earth, the ground will curve away beneath you. So as long as you're above the atmosphere, about 100 kilometers up, you'll be able to stay up there in orbit. This is what the ISS does, falling around Earth, expending energy from time to time to stay fast enough. If we look at orbits in scale, we see that near-Earth orbit is laughably close to Earth. To deploy, for example, satellites or leave for other planets requires another round of energy debt repayment. Getting to orbit is the most difficult part of spaceflight for us right now. For example, if we want to send a rocket to Mars, half the energy is necessary just to get into orbit, and the other half for the 55 million kilometers to Mars. Therefore, to be as effective as possible, rockets aren't built in one giant piece. Instead, we use multi-stage rockets. You don't need to carry an empty fuel tank, so rockets drop it. Rockets today shed their boosters and main stage as they ascend, with each successive stage being its own fully contained rocket, complete with its own engine and fuel. Okay, so this is why getting to space is hard. If you feel all of this seems really complicated, don't worry. It's literally rocket science. This video was made possible in part by a sponsorship by Airbus Safran Launchers and Arianespace, who are getting their new Ariane 6 rocket ready to launch into space in 2020. You can learn more about the rocket here. Since the Industrial Revolution, humans have released over 1.5 trillion tons of carbon dioxide or CO2 into the Earth's atmosphere. In the year 2019, we were still pumping out around 37 billion more. That's 50% more than the year 2000 and almost 3 times as much as 50 years ago. And it's not just CO2. We're also pumping out growing volumes of other greenhouse gases such as methane and nitrous oxide. Combining all of our greenhouse gases, we're emitting 51 billion tons of carbon dioxide equivalents each year. And emissions keep rising. But they need to get down to zero. In recent years, the consequences have become more serious and visible. Almost every year breaks some horrible record. We've had more heat waves, the most glaciers melting, and the lowest amount of ice ever recorded at the North Pole. Of the last 22 years, 20 have been the hottest on record. The only way to limit this rapid climate change is to decrease our collective emissions quickly. But although all countries agree on this goal in principle, they do not agree who is responsible or who should bear the heaviest load. The developed countries point at their own efforts to reduce emissions and the fact that the large developing countries on the rise, especially China, are currently releasing much more CO2. On the other hand, developing countries argue that emissions by the West are lifestyle emissions, while for developing countries, they are survival emissions. Others call rich countries hypocrites that got rich by polluting without restraint and now expect others not to industrialize and stay poor. So, who is responsible for climate change and CO2 emissions? And regardless of the past, who needs to do the most today? In this video, we'll talk exclusively about nation-states. We'll look at the fossil fuel industry in another video. Question 1 of 3. Which countries emit the most carbon dioxide today? In 2017, humans emitted about 36 billion tons of CO2. More than 50% came from Asia. North America and Europe followed with 18% and 17%. While Africa, South America and Oceania together only contributed 8%. China is by far the world's largest emitter, with 10 billion tons of CO2 every year, or 27% of global emissions. It's followed by the USA with 15% and the European Union with around 10%. Together, this is more than half of the world's CO2 emissions. So it's clear that without the willingness and action of these 3 industrial blocs, humanity will not be able to become carbon neutral and prevent severe climate change. Next on our list is India at 7%, Russia at 5%, Japan at 3%, and Iran, Saudi Arabia, South Korea and Canada all just short of 2%. Together with the first 3, the top 10 are responsible for 75% of global emissions. But if we only look at the current situation, we're not getting the full picture. Question 2 of 3. Which countries have emitted the most in total? If we look at emissions throughout history until today, the outlook changes drastically. The US and the EU both knock China off the top spot. The US is responsible for 25% of the world's historical emissions, emitting 400 billion tons, mostly in the 20th century. In second place is the EU at 22%. China comes in third at just under 13%, around half of the USA's contribution. India's contribution shrinks to 3% along with the whole of Africa and South America. The UK is responsible for 1% of annual global emissions, but takes 5% of the historical responsibility. Germany, producing 2% of emissions per year today, has contributed almost 6%, as much as the whole of Africa and South America combined. So the narrative that rapid climate change is really the responsibility of the developing world is hard to defend if facts matter to you. But this is still not the whole story, because focusing on countries mixes two things: population numbers and total emissions. If a country has more people in general, its emissions are of course higher. Things look very different if we look at individuals like you, dear viewer. Question 3 of 3. Which countries emit the most carbon dioxide per person? The average human is responsible for around 5 tons of CO2 each year. But averages can be misleading. The countries with the largest CO2 emissions per person are some of the world's major oil and gas producers. In 2017, Qatar had the highest emissions at a hefty 49 tons per person, followed by Trinidad and Tobago, Kuwait, the United Arab Emirates, Brunei, Bahrain, and Saudi Arabia. But those are outliers. Australians have one of the highest carbon footprints per person, 17 tons a year. That's more than triple the global average and slightly more than the average US, American and Canadian at 16 tons. The Germans do a little better at close to 10 tons, but this is still twice the global average. China may be the world's largest emitter, but it's also the world's most populous country with over 1.4 billion people, 18.5% of the world population. Per person, it's above average at 7 tons. Historically, CO2 emissions have been closely tied to a high standard of living. Wealth is one of the strongest indicators of our carbon footprint because as we move from poor to rich, we gain access to electricity, heating, air conditioning, lighting, modern cooking, cars or planes, smartphones, computers, and interact with people across the world online. The enormous rise of China's CO2 emissions is coupled with the greatest reduction of poverty in history. If we order CO2 emissions by income, we see that the richest half of countries are responsible for 86% of global emissions and the bottom half for only 14%. The average German emits more than 5 times as much as the average Indian. In just 2.3 days, the average American emits as much as the average Nigerian in a year. And not only that, the harsh reality is that it's the countries that contribute least to the problem that stand to lose the most from rapid climate change. The developing world will be hit the hardest. The consequences could be food insecurity, conflicts over resources, harsher and more frequent natural disasters, and large climate refugee movements. Question 4 of 3. So who should take responsibility? Many of today's richest countries are in a convenient position. They have become rich over centuries of fossil fuel burning and industrial production. They have a large historical footprint, and their wealth means they still emit a lot per person. But their country's annual emissions are now dwarfed by other countries because the giant that is China is finally catching up, and other giants like India are on their way. Many Germans, for example, wonder how, if Germany only accounts for 2% of yearly emissions, it can have a meaningful impact on reducing emissions. The answer is simple. For one, the richest countries have the resources, highly educated workforces and technology to develop low-cost, low-carbon solutions and spread them around the world. If we don't want poorer countries to become as fossil fuel dependent as we are, we need low-carbon technology to be cheap and available. And we're getting there. The cost of renewables is falling quickly, and a variety of solutions are on the horizon for many different sectors. But it needs to happen much faster. If the rich countries of the West decide to seriously tackle rapid climate change, the rest of the world would follow, because it has no choice. Just like when the European Union enforced energy efficiency standards for technology, the rest of the world adopted them too because they wanted to be able to continue trading with the bloc. Still, this doesn't absolve others of their responsibility. China is the largest CO2 emitter today, and it's China's responsibility to grow in a way that will make it possible to transition to a zero-carbon world in time. Others acting irresponsibly yesterday is a horrible excuse for repeating the same mistakes today. Climate change is a global problem, and no country alone can fix it. Working out who's responsible is not as simple as it seems, and in a way it's a daft question, but one that has played international politics for decades. In the end, it's pretty simple. Everybody needs to do the best they can. And right now, we are all not doing that. But we can begin today. By the end of the 21st century, humanity is becoming desperate. Decades of heat waves and droughts have led to unusually poor harvests, while the warming oceans yield fewer fish each year. In the tropical zones, millions suffer from famines, and resource wars have made millions more flee to the north. As things quickly get worse, in an act of desperation, the world's governments decide to enact an emergency plan. It's far from certain that a grim scenario like this will play out, but the failure of world leaders to effectively address climate change makes it far from impossible. So, in the near future, it might become necessary to try something radical to slow down rapid climate change. Geoengineering. Interventions so massive in scale that they might undo centuries of human behavior, or make everything much worse. What is geoengineering? Is it really an option? And what if it goes wrong? Geoengineering methods vary from fantastic ones like constructing giant light sails in space to seeding clouds with salt, or wilder ones like fertilizing the oceans with iron to speed up the growth of trillions of algae cells. In this video, we'll focus on an intervention we could see during our lifetimes: stratospheric aerosol injection. A clunky term that means spraying stuff very high up in the atmosphere to keep the sun away. Keeping the sun away. CO2 doesn't heat up the planet on its own. Almost all of the energy on Earth comes from the sun in the form of electromagnetic radiation. About 71% of this energy is absorbed by the Earth's surface and atmosphere. This absorbed energy is emitted again as infrared radiation, and CO2 is able to trap this infrared radiation and keep it in the atmosphere for a while. You can compare this effect with snuggling under a blanket in the morning. Even in a really cold room, your body emits infrared radiation, and the air between your body and the blanket traps it and creates a warm and comfy feeling. So one way to cool down the planet would be to prevent energy from getting trapped under our planet blanket, which is already happening naturally. About 29% of the solar radiation hitting Earth is reflected back to space by bright surfaces like ice, deserts, snow, or clouds. More reflection, less energy, less warming. We can look at nature for inspiration. Specifically, the 1991 Mount Pinatubo eruption, the second largest volcanic eruption of the 20th century. Aside from massive devastation and almost 900 dead, scientists noted its strong impact on the global climate. The explosion ejected millions of tons of particles and gas as high as the stratosphere, which hung around there for a while. The stuff that's interesting for geoengineering is sulfur dioxide, a nasty-smelling and invisible gas. High in the atmosphere, it produced a haze of sulfuric acid droplets that mixed with water and created giant veils. These veils reduced the sunlight reaching Earth's surface by roughly 1%. global average temperatures dropped by 0.5 degrees Celsius. It took 3 years until this cooling effect had stopped. Humans could imitate this process by injecting sulfur particles directly into the stratosphere. According to some scientists, this might be surprisingly easy to do, and we don't even need a lot of new technology for it. According to one study, it also might be pretty cheap compared with the costs of rapid climate change. A small fleet of specialized aircraft could ascend once a year and distribute aerosols along the equator from where they would be spread around the world. Projections assume that injecting between 5 and 8 megatons of material per year would reflect enough sunlight to slow down or even stop global warming, giving us precious time to transition away from fossil fuels. Unfortunately, there might be a few unhappy side effects. There are a number of potential issues with aerosol injections. Rainfall patterns could change, which could negatively affect agriculture and cause famine. Billions of people could be affected in the worst case. Also, after the 1991 Mount Pinatubo eruption, the acid water veils not only cooled down the surface, they also heated up the stratosphere. As it turns out, acid is bad for the ozone layer, and the ozone hole over Antarctica was the largest it has ever been. Injecting sulfur particles over decades could have a similar effect. Scientists have already suggested using a combination of different minerals that might have much less harmful effects on the ozone layer, but more research and experiments need to be done to make sure this could work. But even if we don't damage the ozone layer, there are other risks. Politicians and industry might use the cooling effect as an excuse to delay the switch to a carbon-neutral economy. Even if geoengineering slows down global warming, humanity is still adding extra CO2 to the atmosphere. More CO2 in the air means that the oceans absorb more CO2, which makes them more acidic. This is already beginning to be deadly to huge ecosystems like coral reefs, and the longer this continues, the more severe the effects will be. But it gets worse. Once we start pumping particles into the atmosphere on a massive scale, we might be forced to do so for a long time, or we could risk a termination shock. What that means is that if humanity continues to enrich the atmosphere with CO2, but at the same time prevents the planet from heating up by blocking solar radiation, we're sitting on a time bomb. Once we stop geoengineering, the natural cycle will take over again and Earth would heat up. But after a few decades of keeping the planet artificially cold while still releasing massive amounts of CO2, it would heat up much quicker. An increase in temperature that would take 50 years today could happen in just 10 years. Such a temperature shock in such a short time would disrupt every major system on Earth so much that it would be impossible to adapt in time. The worst-case scenario could be dramatic famines and the rapid destruction of ecosystems. Humanity might survive, but the survivors would inhabit an unfamiliar and hostile world. The best-case scenario is that once the world has finally fully understood the existential danger of rapid climate change, geoengineering can buy us a crucial decade or two. Time to transition our economies and maybe even pull CO2 out of the atmosphere, maybe with technologies that we'll discuss in a future video. Conclusion. Geoengineering is a scary concept. It's not a solution to climate change, and it might even be a welcome excuse for the fossil fuel industry to delay the end of the fossil fuel age. Over the last few decades, geoengineering has been so controversial that it's stopped many scientists from doing the experiments necessary to understand it better. But blankly opposing geoengineering is short-sighted. The sad truth is, we are already running a geoengineering experiment. We're testing how fast the world changes if we add about 40 billion tons of CO2 each year. This experiment is about to get really exciting. Hopefully, we'll never have to use geoengineering. But if we need to in the future, we better have done the science. We better be prepared. Or a panicking humanity might accidentally press the self-destruct button. We've found a new planet, home to octillions of the most extreme beings living in the most absurd and deadly hellscape. In absolute darkness, crushed by the weight of mountains, starved of oxygen, cooked alive, bathed in acid, salt or radiation. And yet, they live for thousands, perhaps millions of years. It turns out, this planet is not in space, it's inside the crust of Earth. This is the deep biosphere, and we basically learned that it exists yesterday. Its volume is at least twice as large as all the Earth's oceans, home to more microbes than the rest of the entire planet. Their total biomass is more than 20 times greater than all humans, livestock and animal wildlife. Let's descend into this mad, deadly world where none of the rules we thought are mandatory for life apply. Going deeper and deeper. Deep life seems to be everywhere we look, below the oceans, near volcanoes, beneath the glaciers of Antarctica, under any landscape we can imagine, and anywhere we live. We'll use a special duck science drill and start our journey in familiar territory, on land, in the soil where plants grow and animals roam. If Earth were an onion, this is the very top of the very top layer. Soil is a lavish four-way partnership of air, water, minerals and organic matter bathed in endless energy. Life lives in luxury here. Plants exploit this paradise and produce more than 30 times the biomass of all of Earth's animals each year, in a constant cycle of growth and decay. Only a tiny fraction of the biomass is buried deeper in the ground, supplying juicy resources for almost 500 million years. As we dig deeper, most of the air has been squeezed out and we cross the water table into a zone saturated with groundwater, rich in minerals and some organic matter. Roots from the most ambitious plants reach down here, and the most common inhabitants are scavengers living off decay. This layer can be pretty cold because it's still slowly warming up from the most recent ice age. We reach bedrock, a foundation of solid rock for all the less solid stuff above, home to fractures filled with water. It can be exposed to the surface or buried hundreds of meters below stuff. Here in the dense bedrock, we're in a weird planet inside the planet, the most thrilling zone of the deep biosphere. As we drill further down, temperatures gradually begin to rise, and soon it gets really hot and the pressure rises. Underneath 400 meters of rock, the pressure is similar to the surface of Venus. We drill faster now, down to 1,000 meters, deeper than the Burj Khalifa is tall. It's about 30 degrees Celsius, and there's almost no free oxygen left. We continue and finally stop almost 4 kilometers down. Above us, pressing solid rock weighing tens of thousands of tons, with pressures as intense as at the bottom of the Mariana Trench. Down here, it's on average 120 degrees Celsius, even hotter if a magma plume is nearby. The heat is a leftover from Earth's formation and from the decay of radioactive elements like thorium and uranium that shower the crust with a constant wave of radioactivity. To make things worse, some rocks are mixed with extreme amounts of salt. Hell. And yet, life is thriving inside rock. If we zoom in, we see that solid rock is not actually solid, it's traversed by cracks, voids and tiny pores. Sandstone, limestone or basalt are so porous that up to 40% of their volume is actually empty space. But even much denser rocks like granite can be split open by cracks and fractures. We've found a gigantic planet-spanning system of microcaves, free real estate filled with water and hardcore microbes. And these caves are moving. Just like the atmosphere is constantly mixing air to create weather, down here rocks are mixing to create rock weather. Submerged mountain ranges are shifting and ripping, crashing and merging. Continents smash into each other with the energy of millions of nuclear weapons, but as slow as your fingernails grow. Countless tiny and not so tiny earthquakes rip open tiny new fissures and passageways, creating new spaces for life and closing others off forever. In this hot, moving pressure cooker, minerals are forged and baked, and organic molecules are created and destroyed. An insane menu for anyone brave enough to try to survive down here. Let's venture into the system of tiny caves and meet some of them. The most extreme living things. We think that octillions of microbes live down here, and naturally they are pretty hardcore. The doomsday preppers of the underworld. Some have big, bulky genomes living entirely on their own, basically forming their own ecosystem, like the bacterium Desulforidus aurex viator. It synthesizes its own food by nibbling carbon or sulfur from the rock and turning it into organic substances. If the conditions get too extreme, or if there's no food around, it kills itself to survive by forming an endospore. It divides into a big and a small part and swallows the small part again, forming a cell within a cell. The outer cell then sheds its water and kills itself, leaving the spore to float around, maybe for thousands of years, until it finds a good place to spring to life again. Others like some company, like the archaea with the clunky name Altiarchaeum hemiconnexum, that have a rare double membrane covered in weird materials that protect them against the extremes. They shoot out nano-sized grappling hooks to tether themselves and seem to live in cracks and fissures filled with water completely devoid of oxygen, harvest carbon dioxide to create biomass, and may sort of eat hydrogen. The conditions in the deep biosphere are so harsh that other microbes share the hard work by forming consortia. They knit themselves together in a biofilm, a very thin, sticky net that shields them against the extremes. They are miniature cells, often with a small genome, but each good at one thing. One type of microbe eats methane and excretes its electrons. A second type eats these electrons and converts sulfate into sulfite that's then eaten by a third microbe, and so on. Some eat iron, others use electrons to turn nitrogen or carbon dioxide into biomass. Life down here found ways to use stuff that's poisonous to most animals to make food and energy. But still, life is incredibly hard, and resources and energy are super hard to come by. So the most intense strategy for survival down here is to live forever. Like monks who've taken a vow of poverty, deep microbes consume very little and conserve their energy. Their metabolism is up to 1 million times slower than microbes at the surface. They had a meal when you were born and are still digesting it. For most of their life, they exist in a slow limbo. Some even slowly cannibalize themselves, until a sudden influx of resources arrives by pure chance, and then they spring into action and reproduce. With this lifestyle, it seems that extreme microbes can live for centuries, maybe even for millions of years. If they're not hunted to death, of course. Because kilometers deep in limestone habitats, there seem to be spaces big enough for multicellular predators. We've found asexual worms, 100 times longer than microbes, hunting and devouring bacteria. It's not clear if they originated down here or if many earthquakes opened up fractures for water to carry them into the deep. But there are other fierce predators like rotifers or arthropods in the depths, hunting immortal microbes. We wish we could tell you more insane things about life in the deep biosphere, but there's a problem. We don't know that much yet. For one, we can't really get a good look under kilometers of rock. Drilling down could contaminate the samples with microbes from the surface. We've found living ones in deep mines and brought them into the lab, but it's pretty hard to simulate the conditions they feel comfy in boiling hot water, squeezed under mountains, submerged in deadly chemicals, and still see them through a microscope. And the microbes live so slowly for so long that nothing might happen. A lot of what we know about them we got from turning them into a slurry and looking at what their genes could do, like breathing nitrogen or eating methane. We know that the diversity of life in the deep biosphere must be staggering, and that some of the most hardcore and extreme beings live down there. This is a proper frontier of science, super hard to study, and most of what we know we've learned in just the last 20 years. There is so much more undiscovered mystery for us that could bring us progress in medicine, energy, the climate, and more. Let's end by moving our gaze from the inside to the outside again. Since we now know how extremely large the deep biosphere is and how life down there survives without light, oxygen, sane temperatures, or not being covered in poison, could there be deep biospheres all over the universe? Maybe all you need is a planet or moon with internal heat or radiation, and a chemical composition that allows microbes to build the parts they need. Some scientists suggest there could be 10 of them in the solar system, hiding beneath a seemingly dead and frozen surface. So as we learn more and more about the life below our feet, we may accidentally learn about life in the universe. Today, we're doing something different. Our friend John Green will read a story from his podcast, The Anthropocene Reviewed. We hope you enjoy it, and we'll be back with a regular video soon.
So, if you've ever been or had a child, you will likely already be familiar with hand stencils. They were the first figurative art made by both our kids. Somewhere between the ages of 2 and 3, my children spread the fingers of one hand out across a piece of paper, and then, with the help of a parent, traced their 5 fingers. I remember my son's face as he lifted his hand and looked absolutely shocked to see the shape of his hand still on the paper, a semi-permanent record of himself. I am extremely happy that my children are no longer 3, and yet to look at their little hands from those early artworks is to be inundated with a strange, soul-splitting joy. Those pictures remind me that they are not just growing up, but also growing away from me, running toward their own lives. But of course, that's meaning I am applying to their hand stencils, and that complicated relationship between art and its viewers is never more fraught than when we are looking deeply into the past. In September of 1940, an 18-year-old mechanic named Marcel Ravidat was walking his dog Robot in the countryside of southwestern France when the dog disappeared down a hole. Robot eventually returned, but the next day Ravidat went to the spot with 3 friends to explore the hole. And after quite a bit of digging, they discovered a cave with walls covered with paintings, including over 900 paintings of animals, horses, stags, bison, and also species that are now extinct, including a woolly rhinoceros. The paintings were astonishingly detailed and vivid, with red, yellow, and black paint made from pulverized mineral pigments that were usually blown through a narrow tube, possibly a hollowed bone, onto the walls of the cave. It would eventually be established that these artworks were at least 17,000 years old. 2 of the boys who visited the cave that day were so profoundly moved by the art they saw that they camped outside the cave to protect it for over a year. After World War II, the French government took over protection of the site, and the cave was opened to the public in 1948. When Picasso saw the cave paintings on a visit that year, he reportedly said, "We have invented nothing." There are many mysteries at Lascaux. Why, for instance, are there no paintings of reindeer, which we know were the primary source of food for the Paleolithic humans who lived in that cave? Why were they so much more focused on painting animals than painting human forms? Why are certain areas of the cave filled with images, including pictures on the ceiling that required the building of scaffolding to create, while other areas have only a few paintings? And were the paintings spiritual? Here are our sacred animals? Or were they practical? Here is a guide to some of the animals that might kill you. Aside from the animals, there are nearly 1,000 abstract signs and shapes we cannot interpret, and also several negative hand stencils, as they are known by art historians. These are the paintings that most interest me. They were created by pressing one hand with fingers splayed against the wall of the cave, and then blowing pigment, leaving the area around the hand painted. Similar hand stencils have been found in caves around the world, from Indonesia to Spain to Australia to the Americas to Africa. We have found these memories of hands from 15 or 30 or even 40,000 years ago. These hand stencils remind us of how different life was in the distant past. Amputations, likely from frostbite, are common in Europe, and so you often see negative hand stencils with 3 or 4 fingers, and life was short and difficult. As many as 1/4 of women died in childbirth. Around 50% of children died before the age of 5. But they also remind us that the humans of the past were as human as we are, their hands indistinguishable from ours. These communities hunted and gathered, and there were no large caloric surpluses, so every healthy person would have had to contribute to the acquisition of food and water, and yet somehow they still made time to create art, almost as if art isn't optional for humans. We see all kinds of hands stenciled on cave walls, children and adults, but almost always the fingers are spread, like my kids' hand stencils. I'm no Jungian, but it's fascinating and a little strange that so many Paleolithic humans who couldn't possibly have had any contact with each other created the same paintings the same way, paintings that we are still making. But then again, what the Lascaux art means to me is likely very different from what it meant to the people who made it. Some academics theorize that the hand stencils were part of hunting rituals. Then there's always the possibility that the hand was just a convenient model situated at the end of the wrist. To me, though, the hand stencils at Lascaux say, "I was here. they say, "You are not new." And because they are negative prints surrounded by red pigment, they also look to me like something out of a horror movie, like ghostly hands reaching up from some bloody background. They remind me that, as Alice Walker wrote, all history is current. The Lascaux Cave has been closed to the public for many years now. Too many contemporary humans breathing inside of it led to the growth of mold and lichens, which has damaged some of the art. Just the act of looking at something can ruin it, I guess. But tourists can still visit an imitation cave called Lascaux 2, in which the artwork has been meticulously recreated. Humans making fake cave art to save real cave art may feel like peak Anthropocene behavior, but I have to confess that even though I am a jaded and cynical semi-professional reviewer of human activity, I actually find it overwhelmingly hopeful that 4 teenagers and a dog named Robot discovered a cave with 17,000-year-old handprints, that the cave was so overwhelmingly beautiful that 2 of those teenagers devoted themselves to its protection, and that when we humans became a danger to that cave's beauty, we agreed to stop going. Lascaux is there. You cannot visit. You can go to the fake cave we've built and see nearly identical hand stencils, but you will know this is not the thing itself, but a shadow of it. This is a handprint, but not a hand. This is a memory that you cannot return to. All of which makes the cave very much like the past it represents.
Planet Earth is the home of every life form known to us in the universe. Its age is about a third of the age of the universe, and, admit it, it is a thing of beauty. A slightly squashed sphere with a heavy metal core and a lighter surface crust wrapped in a thin sliver of sweet air to breathe, with vast oceans, fertile plains, magnificent mountains, freshwater rivers, streams, lakes and aquifers, orbiting a star which warms us and gives us energy. But how did our home come into existence, and what's it made of? $4.6 billion years ago, Earth was created from the remnants of dead stars that collected in a giant dirty gas cloud. The gas cloud became denser in its center and formed an accretion disk. Small particles started clumping together and building larger and larger objects until they formed the objects we call planets today. This process took 10 to 20 million years and is still not very well understood. At about this time, when the solar system was young and chaotic, a giant object about as big as Mars collided with our home. The impact was violent, and if the object had been more massive, it might have destroyed Earth. Material from Earth was smashed out into orbit and formed the Moon, which is the biggest satellite in relation to its planet in the solar system. At this time, Earth was a hot hell, constantly being hit by asteroids, with seas of lava and a toxic atmosphere. But something was about to change drastically. Earth cooled down. Water from the inside of the Earth wandered to the surface and rained down on Earth, only to vaporize again and become clouds. Millions of asteroids brought more and more water to our planet. All the water on Earth has about this volume compared to Earth. Today, the surface of Earth is 71% water and 29% land. 97.5% is saline water, while only 2.5% is freshwater. The freshwater is 69% ice and snow, 30% are groundwaters, and only about 1% make up the remaining groundwaters. But even this small part is mostly frozen. Only a tiny part of our water is actually lakes and rivers, and an even tinier part is bound in living things. So, gradually the Earth cooled down and the surface formed a thin crust. But inside the Earth, hot rock continued to swirl about, moving the crust from below and breaking it apart. This process is called plate tectonics and is happening right now. We'll make a whole video about it in the future. For now, let's just say that the crust of Earth consists of separate giant plates that move around. As they meet, they crumble and create mighty mountains, or violently plunge back down deeper into Earth, creating deep trenches. That's the way the highest place on Earth was formed, Mount Everest, and the deepest, the Mariana Trench. From our perspective, Earth's mountains and trenches are mighty indeed, but when you look at the Earth in cross-section, you can see how tiny they actually are. The part we stand on is the crust, which is about 50 kilometers thick, though it can vary between 5 and 70 kilometers. By the way, the deepest hole ever drilled by man is 12.262 kilometers deep. After the crust comes the mantle. It's a silicate rocky shell and about 2,900 kilometers thick. The mantle consists of the upper mantle and the lower mantle. The upper mantle has different regions too. Its upper part, which is viscous and carries the crust, is called the lithosphere. After that, there comes the asthenosphere, which consists of less mobile, mostly solid material. The lower mantle reaches deep down to the outer core of Earth. Earth's outer core is a liquid layer of iron and nickel, about 2,266 kilometers thick. Temperatures vary from 4,000 degrees Celsius to 5,700 degrees Celsius. And in the center is the inner core. It's mostly solid, a ball made of an iron-nickel alloy, with a radius of about 1,200 kilometers, 70% the size of the Moon and about the temperature of the surface of the Sun. It is slowly growing at an estimated rate of about 1 millimeter per year. Now for some perspective. This small layer of crystallized milk products of former molten mantle is where we live. Then there's Earth's magnetic field. It's an invisible phenomenon that diverts high-energy particles coming from the Sun and other sources, allowing for a stable environment with comparatively little radiation impact on Earth. But why is it there? Actually, we don't really know a terrible lot about that. We know it has something to do with the core of the Earth. Inside this metal sphere, large electrical currents flow in complicated patterns. They cause a magnetic field that sort of stabilizes itself according to the laws of electrodynamics. This entire system is called the dynamo. But don't let us fool you into thinking we have it all figured out. Speaking of breathtaking information, what about the airy stuff that surrounds us? By volume, dry air consists mostly of nitrogen, oxygen, argon, carbon, a variable amount of water vapor, and small amounts of other gases. Humans are very dependent on the lowest layer of the atmosphere, the troposphere, where the weather is. It's 12 kilometers thick on average. Above that is the stratosphere, which is where the ozone layer protects us from the sun's most aggressive type of light. Above that is the mesosphere, the coldest place on Earth, with an average temperature around minus 85 degrees Celsius. At about 80 kilometers up, the thermosphere starts. The transition to space is a fluent one without clear borders, but humans decided that space starts here. At about 100 kilometers, Earth stops and space begins, though the atmosphere extends a bit further. In this region we find the ionosphere, the aurora borealis, and the ISS. And the outermost layer is the exosphere, stretching up to 10,000 kilometers. It merges fluently with outer space where there's no atmosphere at all. The atoms and molecules in this area are so far apart that they can travel hundreds of kilometers without colliding with each other. Okay, humans in their present form have only been around for 200,000 years. That's 0.004% of Earth's history. Not long, really. And here we are now, living in a thin, moist layer on a small, wet rock. We call this rock Earth. It is the product of the universe's deepest workings, the result of a constant process of creation and destruction, happening all over the universe all the time, helped by chance, the laws of the universe, and random events. We are really lucky. 3 reasons why we should continue using nuclear energy. 1. Nuclear energy saves lives. In 2013, a study conducted by NASA found that nuclear energy has prevented around 1.8 million deaths. Even if you include the death tolls from Chernobyl and Fukushima, nuclear energy ranks last in death per energy unit produced. While nuclear waste is really toxic, it's usually stored somewhere, while the toxic byproducts of fossil fuels are pumped into the air we breathe every day. So, just by reducing the amount of fossil fuels burned, countless cases of cancer or lung disease and accidents in coal mines have been avoided. If we can choose between lots of dangerous stuff being put into a deep hole and lots and lots and lots of dangerous stuff being pumped into the atmosphere, the former seems more logical. Nuclear energy feels way more dangerous though. Single catastrophic events burn into our memory, while coal and oil kill silently. It's like the death rate of flying versus driving. Even in the best-case scenario, it would take at least 40 years to switch to 100% renewable energy. So for as long as we continue using fossil fuels, nuclear energy will save way more lives than it destroys. 2. Nuclear energy reduces CO2 emissions. Nuclear energy is arguably way less harmful to the environment in terms of climate change than fossil fuels, our main source of energy. Since 1976, about 64 gigatons of greenhouse gas emissions have not been pumped out thanks to nuclear energy. And by the mid-21st century, that could amount to an additional 80 to 240 gigatons. Humanity's energy consumption is rising steadily. According to US government projections, China alone will add the equivalent of a new 600 megawatt coal plant every 10 days for the next 10 years. China already burns 4 billion tons of coal each year. Coal is cheap, relatively abundant, and easy to get to, so it's not likely that humanity will stop using it soon. Nuclear energy might be the only way of dampening the effects of climate change and preventing a catastrophic man-made global warming. Compared to the other things we do, nuclear energy is relatively clean. So even if it is a good idea to quit nuclear energy long-term, it might be a good solution for the next 100 years or so compared to the alternatives. 3. New technologies. Maybe technology will solve the problem of nuclear waste and dangerous power plants. The nuclear reactors we've used so far are mostly outdated technology because nuclear innovation stopped in the 1970s. There are models like the thorium reactor that could solve the problem altogether. Thorium is abundant, really hard to turn into nuclear weapons, and up to 2 orders of magnitude less wasteful than current nuclear reactors. The waste material might also be only dangerous for a few hundred years, in contrast to a couple of thousand years. 1 ton of thorium is estimated to provide the same amount of energy as 200 tons of uranium or 3.5 million tons of coal. So while we cannot know for sure if alternative nuclear technology will keep its promises, shouldn't we at least do more research before we forego an opportunity to solve lots of humanity's current problems? It might not be an easy challenge, but that hasn't stopped us before. So, should we use nuclear energy? There are risks involved in any great human endeavor, and we have to make an informed decision rather than rely on gut feeling. 3 reasons why we should stop using nuclear energy. 1. Nuclear weapons proliferation. Nuclear technology made a violent entrance onto the world stage. Just 1 year after the world's first ever nuclear test explosion in 1944, 2 large cities were destroyed by just 2 single bombs. After that, reactor technology slowly evolved as a means of generating electricity, but it's always been intimately connected with nuclear weapons technology. It's nearly impossible to develop nuclear weapons without access to reactor technology. In fact, the Nuclear Non-Proliferation Treaty serves the purpose of spreading nuclear reactor technology without spreading nuclear weapons with limited success. In 40 years, 5 countries have developed their own weapons with the help of reactor technology. The fact of the matter is that it can be very hard to distinguish a covert nuclear weapons program from the peaceful use of nuclear energy. In the 1970s, the big nuclear powers were happily selling peaceful technology to smaller countries, which then developed weapons of their own. The road to deadly nuclear weapons is always paved with peaceful reactors. 2. Nuclear waste and pollution. Spent nuclear fuel is not only radioactive, but also contains extremely poisonous chemical elements like plutonium. It loses its harmfulness only slowly over several tens of thousands of years. And there is also a process called reprocessing, which means the extraction of plutonium from spent nuclear fuel. It can be used for 2 purposes: to build nuclear weapons or to use it as new fuel. But hardly any of it is used as fuel because we don't have the right kind of reactors for that. A milligram will kill you, a few kilograms make an atomic bomb, and even an inconspicuous country like Germany literally has tons of the stuff just lying around because reprocessing sounded like a good idea decades ago. And where will all the waste go? After dumping it into the ocean was forbidden, we've tried to bury it, but we can't find a place where it will definitely stay secure for tens of thousands of years. Over 30 countries operate nearly 400 reactors, managing several hundred thousands of tons of nuclear waste, and only one is currently serious about opening a permanent civilian waste storage, tiny Finland. 3. Accidents and disasters. Over 60 years of nuclear power usage, there have been 7 major accidents in reactors or facilities dealing with nuclear waste. 3 of those were mostly contained, but 4 of them released significant amounts of radioactivity into the environment. In 1957, 1987 and 2011, large areas of land in Russia, Ukraine and Japan were rendered unfit for human habitation for decades to come. The number of deaths is highly disputed, but probably lies in the thousands. These disasters happened with nuclear reactors of very different types in very different countries and several decades apart. Looking at the numbers, we may as well ask ourselves, are 10% of the world's energy supply worth a devastating disaster every 30 years? Would 30% be worth another Fukushima or Chernobyl somewhere on Earth every 10 years? What area would have to be contaminated so we say no more? Where is the line? So, should we use nuclear energy? The risks may outweigh the benefits, and maybe we should stop looking into this direction and drop this technology for good. If you want to hear the other side of the argument, or a short introduction to nuclear energy, click here. Our home is burning. Rapid climate change is destabilizing our world. It seems our emissions will not fall quickly enough to avoid runaway warming, and we may soon hit tipping points that will lead to the collapse of ecosystems and our civilization. While scientists, activists, and much of the younger generation urge action, it appears most politicians are not committed to doing anything meaningful, while the fossil fuel industry still works actively against change. It seems humanity can't overcome its greed and obsession with short-term profit and personal gain to save itself. And so for many, the future looks grim and hopeless. Young people feel particularly anxious and depressed. Instead of looking ahead to a lifetime of opportunity, they wonder if they will even have a future or if they should bring kids into this world. It's an age of doom and hopelessness, and giving up seems the only sensible thing to do. But that's not true. You are not doomed. Humanity is not doomed. Despite the seriousness of the situation, for years positive trends have accumulated, and there is finally some good news and a clear path towards our collective climate goals. Welcome to our TED Talk. Please watch this video to the end. Check out our detailed sources afterwards to learn more. Okay, let's start with the scariest things. Cancelling the apocalypse. Some of the most widely shared stories about climate change are that it is an existential threat, the end of human civilization, and maybe even our own extinction event, and that it's basically unavoidable now. But what does science actually say? As of 2022, the global average temperature has risen 1.2 degrees Celsius compared to pre-industrial times. Limiting warming to 1.5 degrees was the most ambitious goal of the Paris Agreement, but we are not likely to meet it. Already with the warming we have today, hot places will get hotter, wet places wetter, and the risk and strength of extreme weather events increase significantly. Warming beyond 2 degrees makes all of these extremes more extreme. Extreme weather events more common, with more ecosystems under major pressure. Some will not survive. At 3 degrees, significant parts of Earth, especially in developing countries, might become unable to feed their populations. Heat waves will become a major global issue. Large-scale natural systems will break down. The scale and frequency of hurricanes, fires, and droughts will further increase and cause trillions in damage. Poor regions and subsistence farmers will be hit the hardest. Hundreds of millions of people will need to leave their homes. In the 4 to 8 degree range, the apocalypse begins. The hothouse Earth, where things change so quickly that it may become unable to support our large human population and billions may perish, leaving the rest on a hostile alien planet. A decade ago, for lack of action and perspective, many scientists assumed a 4+ degree world was our future, and a lot of public communication focused on exactly this future path. Luckily, it's much less likely that this version of the apocalypse will come to pass. If current climate policies stagnate, we're likely to end up with warming of around 3 degrees Celsius by 2100. which is scary and tragic and far from acceptable. But this is actually good news. How? In the last decade, we've seen enough progress that most scientists now think that we have likely avoided apocalyptic climate change. Although substantial risk still remains, we can pretty confidently say that humanity isn't going anywhere. Civilization might have to change, but it will endure. Which begs the question, what has changed over the last 10 years, and is this really good news? The invisible shift. You probably know this story. The last decade has been an immense failure for climate policies around the world. Instead of passing comprehensive, binding bills that would meaningfully reduce emissions, we mostly did nothing. A lost decade with one negative record after another. And this story is true, and it's one reason why so many people are giving up. But it is not the whole picture. Despite the lack of climate policies and ongoing lobbying and misinformation campaigns from the fossil fuel industries, there was a lot of progress. Let's go back 20 years to see why today is so different. Between 2000 and 2010, greenhouse gas emissions had grown by 24%, 3 times as much as the increase in the previous decade. Subsidies for fossil fuels aimed at promoting economic growth caused a colossal increase in their consumption. For developing countries like China and India, coal was the cheapest fuel for growth, while rich countries showed little interest in changing their ways. In 2010, many people expected these trends to continue. Instead of decreasing fossil fuel use, its consumption would rise. The next decade turned out to be very different though. First of all, coal burning in developing countries like India has slowed down or leveled off like in China, and it's plummeted in rich countries like the UK and US. Since 2015, 3/4 of planned coal plants have been cancelled and 44 countries have committed to stop building them. 10 years ago, that would have seemed like wishful thinking, but today we can say with confidence, coal is dying. It's just not competitive anymore. Because technologies we thought would remain expensive matured rapidly instead. Renewable electricity has shown explosive progress. In a mere decade, wind energy got 3 times cheaper. Solar electricity is now 10 times cheaper. Cheaper than coal or any other fossil fuel burning power plant, despite the massive subsidies and global infrastructure propping up fossil fuels. 25 times more solar and nearly 5 times more wind electricity is produced today compared with 10 years ago, which is of course not nearly enough. One of the biggest obstacles is the variability of their power output. Renewables need a lot of energy storage to be a reliable power source, like expensive batteries. Amazingly, battery prices have decreased by 97% in the past 30 years, 60% in the last decade alone, which will serve all kinds of green technology like electric cars. You might say, well, that's great, but didn't Kurzgesagt's last climate video say that while wind and solar are nice, we need nothing less than a fundamental transition of our global industrial system? Yes, but luckily the shift goes beyond just the energy sector. Throughout the economy, people are working on improving current technology to lower emissions. We're rapidly replacing old incandescent light bulbs with LEDs that are 10 times more efficient. In 2020, about 7 out of 10 new cars in Norway were electric or hybrid. In 2021, it was already 8 out of 10. And the list goes on, from electric heating and better insulation to ships traveling at half speed to save fuel. Wherever you look, you find scientists, engineers, and entrepreneurs trying to solve some aspect of climate change. Enormous amounts of human ingenuity are being brought to bear on this problem, with more and more people deciding to prioritize preventing rapid climate change. Solutions for low-carbon production of cement, electronics, and steel, and innovations like artificial meat and carbon capture are in the works. The more of these technologies we deploy, the cheaper new and better technology gets. The cheaper they get, the more people use them, and so on. We can see the impact already. The domestic CO2 output of rich countries is falling without a major recession. Since the year 2000, the EU as a whole shows a 21% decrease, Italy 28%, the UK 35%, Denmark 43%. But the best news may be that emissions are no longer necessarily coupled with the economic growth. In the past, this was an inconvenient truth. To get richer, you had to emit more, which led to fierce arguments between developing and developed countries about the fairness of reducing emissions while their populations were still poor. But in the last decade, we've seen that it is possible to increase prosperity without increasing emissions. Emissions in the Czech Republic dropped 13%, while their GDP grew by 27%. France reduced their CO2 emissions by 14%, while increasing GDP by 15%. Romania saw an 8% decrease and 35% growth. And even the largest economy on Earth, the USA, decreased emissions by 4% while growing their GDP by 26%. Some of you may call this a numbers trick, that rich countries are just exporting emissions to poorer nations by moving the dirty parts of their economies like manufacturing. But even when we account for all of our imported goods, the numbers still look positive. It's no longer a matter of having to choose between prosperity and the climate, as it seemed to be a decade ago. Developing countries will profit from that because as rich countries pay for the expensive development of green technologies, they can adopt them more cheaply. They can skip most of the high emission phase that today's rich countries went through. We are at the point where not decarbonizing is a bad business decision. And we haven't even really talked about solutions like carbon capture. In 2000, it didn't really exist. In 2022, that technology does exist and costs around $600 to remove 1 ton of CO2 from the atmosphere. As investment pours in and the technology matures and begins to scale, it's likely that these costs will plummet over the next few decades. So everything's fine then? Well, let's not get carried away. All of these processes are great, but not nearly fast enough. We're still doing way too little, and technology will not magically solve everything. We need to use fewer resources and use them longer, design consumer goods that are repairable and durable, and decrease our energy requirements. We need much better infrastructure, agriculture, and cities. It will still be hard work, especially to get the right policies passed and enacted. But for the first time ever, there are a few trend lines pointing solidly in the right direction. And now imagine if all of this was achieved without proper financial and political support, and despite fossil fuel lobbying. Just think what humanity can do when climate change finally gets the political attention and funding it needs. So is it okay to feel hopeful again? The situation is still dire and serious, so what's the point of focusing on this side of the story? The trap of hopelessness. Climate change can feel overwhelming and make your future seem bleak. The sadness and hopelessness that many people feel is real and very destructive because it causes apathy. Apathy that is only serving the fossil fuel industry that is still delaying change however it can. In a sense, they have weaponized hopelessness. We are now in Phase 4 in the public debate about rapid climate change action. Phase 1 was, climate change is not real. Phase 2 was, climate change is real, but not caused by humans. Phase 3 was, climate change may be caused by humans, but it's not that bad. Phase 4 is, climate change is no longer avoidable. We are doomed, and it doesn't matter what we do. If we want the world to change, we first need to believe that change is possible, and we have an abundance of evidence that it is. Changes to our industrial system are gaining momentum, technology gets better and cheaper, climate change has become a key issue in most free elections. As more and more younger people move into influential positions, they prioritize climate change and work on new solutions. In 2022, most governments not only acknowledge it, but set their own net zero goals in democratic and autocratic countries. The results of years of fighting a steep uphill battle are now clearly visible. The pressure needs to keep increasing to make sure that the promises made today are actually kept. Climate doomerism is the equivalent of giving up, even though you can still prevent not just the worst case, but also mitigate most of the bad things, make changes in time to adapt better, and prevent the poorest from suffering. That is why hopelessness and apathy are so dangerous. If the last, in many ways wasted decade has shown anything, then it's that progress is being made, and that dire scenarios are just predictions, not our sealed fate. As of 2022, based on current global policies, we will end up in a 3 degrees world. Now it's our job to yet again prove the predictions wrong, despite how serious and urgent things are. To turn that 3 degrees into a 2 degrees and then see where we can go from there. For that, we need hope. And we hope we gave you that today, at least a little. That you feel that things are serious, but also that you have a future. That you can have kids without dooming them or the world. That taking action today is worth it. And that despite powerful industries doing everything to delay it, society is changing. If you need a more concrete roadmap of what you can do personally, we're working on a follow-up video to talk about that in greater detail. Doomerism, inactivity, and weaponized hopelessness are the only trump cards left for the powers that don't want change. Don't let them win. A war has been raging for billions of years, killing trillions every single day, while we don't even notice. The war is fought by the single deadliest entity on our planet, the bacteriophage, or phage for short. A phage is a virus, not quite alive, not quite dead. Also, they look as if someone made them up. Their head is an icosahedron, a sort of dice with 20 faces and 30 edges. It contains the genetic material of the virus and often sits on a long tail that has leg-like fibers. There are more phages on Earth than every other organism combined, including bacteria. And they are probably everywhere living things exist. Billions are on your hands, in your intestines, and your eyelids right now. Which might make you nervous since phages are responsible for the majority of deaths on Earth. But you're lucky. While they do commit genocide for breakfast, they only kill bacteria. Up to 40% of all bacteria in the oceans are killed by them every single day. But phages also have major flaws. Like any other virus, phages need a host to survive and reproduce. They're not much more than genetic material in a hull, and they specialize. Usually, a phage has chosen one specific bacteria and maybe some of its very close relatives. These are its prey. Imagine a phage as like a cruise missile that only hunts and kills members of one very unlucky family. When a phage finds its victim, it connects its tail fibers with receptors and uses a sort of syringe to puncture the surface. In a weird motion, the phage squeezes its tail and injects its genetic information. Within minutes, the bacteria is taken over. It's now forced to manufacture all the parts of new phages. They only stop when the bacteria is filled up with brand new phages. In the final step, they produce endolysin, a powerful enzyme that punches a hole in the bacteria. The pressure is so high that the bacteria sort of vomits out all of its insides and dies. New phages are released and begin the cycle anew. In the last few years, bacteriophages have enjoyed the attention of the second deadliest beings on Earth, humans. Recently, we've started looking into injecting millions of them into our bodies because we're sort of getting desperate. We screwed up. In the past, a single cut or a sip from the wrong puddle could kill you. Bacteria were our phages, tiny monsters that hunted us mercilessly. But then, about 100 years ago, we found a solution in nature. By accident, we found fungi that produced a compound that killed bacteria, antibiotics. Suddenly, we had a powerful superweapon. Antibiotics were so effective that we stopped thinking of bacteria as monsters. Only the old and weakest among us were killed by them. We used antibiotics more and more for less and less serious causes. We lost respect for the monsters and the weapon. But bacteria are living things that evolve, and one by one, they started to become immune against our weapons. This continued until we had created what are called superbugs, bacteria immune to almost everything we have. This immunity is spreading across the world as we speak. By 2050, superbugs could kill more humans a year than cancer. The days when a cut or bladder infection or a cough could kill you or your loved ones are coming back. In the US alone, more than 23,000 people die from resistant bacteria each year. But it turns out that phages, our tiny killer virus robots, could save us. We can inject them into our bodies to help cure infections. Hold on, how can injecting millions of viruses into an infection be a good idea? Phages are very, very specialized killers of bacteria. So specialized, in fact, that humans are completely immune to them. we are too different. We encounter billions of phages every day, and we just politely ignore each other. Antibiotics are like carpet bombing, killing everything, even the good bacteria in our intestines that we don't want to harm. Phages are like guided missiles that only attack what they're supposed to. Wait a minute, if we use phages to kill bacteria, won't bacteria develop ways of defending themselves? Well, it's more complex than that. Phages evolve too. There has been an arms race between them and bacteria for billions of years, and so far they're doing great. This makes phages smart weapons that are constantly getting better at killing. But even if bacteria were to become immune against our phage, we still might be able to win. It turns out that in order to become resistant to even just a few species of phages, bacteria have to give up their resistance to antibiotics. We might be able to trap them in a catch-22. This has already been successfully tested with a patient who had no other hope left. The bacteria Pseudomonas aeruginosa, one of the most feared bacteria, infected the man's chest cavity. They are naturally resistant to most antibiotics and can even survive in alcoholic hand gel. After years of suffering, a few thousand phages were directly inserted into his chest cavity together with antibiotics the bacteria were immune to. After a few weeks, the infections had completely disappeared. Unfortunately, this treatment is still experimental, and pharma companies are still reluctant to invest the necessary billions in a treatment that has no official approval yet. But things are finally changing. In 2016, the largest phage clinical trial to date began, and phages are getting more and more attention. And we better get used to it, because the era in which antibiotics have been our superweapon is drawing to a close. It might be a weird concept, but injecting the deadliest being on planet Earth directly into our bodies could save millions of lives. Human society is extremely complex and fragile, built upon various pillars. One of them is the honeybee. 1 out of 3 meals eaten by humans is made possible by honeybees. They are so important that if all the honeybees were to die out, thousands of plants would follow, which could lead to millions of people starving in the following years. On top of that, honeybees have a huge economic impact. The dollar value of plants pollinated by them each year is around 265 billion. Food we take for granted would just stop existing without them, or there would be a massive decrease in productivity. Food including apples, onions, pumpkins, and also plants used for feeding livestock, and thus extremely important for our milk and meat. Einstein is often quoted as having said, "If honeybees die out, humans will follow a few years later." Actually, he probably didn't say that, but there might be some truth in the statement. It's unsettling, but honeybees have started to disappear. Millions of hives have died in the last few years. Beekeepers all over the world have seen an annual loss of 30 to 90% of their colonies. In the US alone, bees are steadily declining, from 5 million hives in 1988 to 2.5 million today. Since 2006, a phenomenon called colony collapse disorder has affected honeybees in many countries, and we're not entirely sure what's causing it. All we know is that it's pretty serious. Over the last few decades, bees have seen an invasion of very dangerous foes. Parasites straight out of a horror movie, like a carapace woody. Microscopic mites that infect the trachea, that's the breathing tubes, of bees. Here, they lay their eggs and feed from the fluids of their victims, weakening them considerably and spending their whole life inside the bees. Or Varroa destructor, a fitting name because they can only reproduce in honeybee hives and are one of the bee's greatest enemies. The female mite enters a honeybee brood cell and lays eggs on the bee larva before it's about to pupate and before the hive bees cover the cell with a wax capping. The eggs hatch and the young mites and their mother feed on the developing bee in the safety of the capped cell. The bee is not normally killed at this stage, just weakened, so it still has enough strength to chew its way through the wax capping and release itself from the cell. As it does, it releases the mother mite and her new offspring from the cell, and these are free to spread across the hive, starting the process over again in a cycle of about 10 days. their numbers grow exponentially, and after a few months this can lead to the collapse of the entire beehive. Once outside of the cell, adult mites also suck the bodily fluids of bees and weaken them considerably. To make things worse, they also transmit viruses that harm the bees even more and can lead to birth defects like useless wings. But there are other threats too, such as viruses and fungi. Under normal circumstances, these phenomena should be manageable and are not enough to explain the horrendous amount of dying going on in bees. Over recent years, new insecticides have been introduced that are deadly to bees. Neonicotinoids, a chemical family similar to nicotine, was approved in the early 1990s as an alternative to chemicals like DDT. They attack insects by harming their nervous systems. Today, they are the most widely used insecticides in the world. Globally, they saw sales of 1.5 billion euros in 2008, representing 24% of the global market for insecticides. In 2013, neonicotinoids were used in the US on about 95% of corn and canola crops, and also on the vast majority of fruit and vegetables like apples, cherries, peaches, oranges, berries, leafy greens, tomatoes, potatoes, cereal grains, rice, nuts, grapes, and many more. Bees come into contact with the toxin while collecting pollen or via contaminated water, often bringing material into the hive where it can accumulate and slowly kill the whole colony. The toxins harm bees in a variety of horrible ways. In high enough doses, it quickly leads to convulsions, paralysis, and death. But even in small doses, it can be fatal. It may lead to bees forgetting how to navigate the world, so bees fly into the wild, get lost and die alone, separated from their hives. If this happens often enough, a hive can lose its ability to sustain itself. We know that neonicotinoids are harmful to bees and that we urgently need an alternative to it. But there are billions of dollars to be made in delaying this. Studies sponsored by the chemical industry magically appear to prove a much lower toxicity to bees compared to those produced by independent scientists. There are even more factors contributing to the demise of bees, like too much genetic uniformity, crop monocultures, poor nutrition due to overcrowding, stress because of human activities, and other pesticides. Each of those factors on its own is a major problem for bees, but together they probably account for colony collapse disorder. With parasites upping their game in recent decades, the honeybees are now fighting for survival. It would be a catastrophe if they lost this fight. This is a conundrum we have to solve if we want to continue living with a relative abundance and diversity of food. Humanity is deeply interconnected with Earth and the other life forms on it. Even if we pretend that we're not, we have to take better care of our surroundings, if not to preserve the beauty of nature, then at least to ensure our own survival. Mars is a disappointing hellhole lacking practically everything we need to stay alive. It looks like we'll only ever have small crews spend a miserable time hidden underground. Except we could terraform it into a green new world. But to solve the planet's problems, we first need to make it worse and turn it into oceans of lava with gigantic lasers. This isn't a far-fetched science fiction tale. Terraforming Mars is possible on the kind of timescale our ancestors built great monuments in. If humanity solves some of its pressing problems and ventures into space to expand into the solar system, this may not be that far off. Okay, so how do we terraform Mars quickly? Well, it's complicated. Mars is dry and has no soil to grow anything. Its atmosphere is too thin to breathe or protect us from radiation, giving you a high risk of cancer. So to turn it into a new home for humanity, we have to give it a proper atmosphere similar to Earth's. It should be made of 21% oxygen, 79% nitrogen, and a tiny bit of CO2 at an average temperature of 14 degrees Celsius and under 1 bar of pressure. We have to create oceans and rivers, and then the ground has to be weathered into fertile soil to host living things. Then we need to install a biosphere on the surface and prevent it all from being undone by installing protective measures that can stand the test of time. It is difficult, but a big laser makes it a lot easier. Challenge 1. The atmosphere. Some 4 billion years ago, Mars had a nice oxygen-rich atmosphere and was home to vast oceans and rivers. It held onto it for several hundred million years before it got blown away. Ultraviolet rays broke down the atmospheric gases and then the oceans until they were swept away by solar wind. Today, Mars is a dry, barren wasteland. Luckily, a sizable portion of the water is frozen in deep reservoirs and in the polar ice caps, enough to create a very shallow ocean. And enormous amounts of oxygen are bound as minerals in the Martian rocks, like the oxygen in the iron oxides that give the planet its rust-red color, as well as carbon dioxide in carbonates. To free these gases, we need to reverse the reactions that lock them away by using thermolysis, which occurs at temperatures as high as on the surface of the Sun. In short, we want to melt the surface of Mars. The best way to do that would be to put lasers in orbit, aiming their beams down on Mars. The most powerful laser today is the ELI-NP, able to produce beams of 10 petawatts of power for a trillionth of a second. To melt Mars, we need a laser twice as powerful that runs continuously. The easiest way is to use a solar-pumped laser that can be powered directly with sunlight. At its core are metal-infused glass rods that absorb energy and release it as a laser beam. If we build an array of mirrors in space about 11 times the size of the United States, we can focus enough sunlight onto them to melt Mars. Let's do it! As the lasers hit the surface, about 750 kilograms of oxygen and some carbon dioxide emerge from every cubic meter of rock melted. If we are efficient, our lasers only need to melt through the top 8 meters of the surface to get enough oxygen. It would look terrifying. The skies would be shrouded in storms, while the ground would glow red-hot, crisscrossed by currents of lava. Tireless laser beams sweep over the landscape, leaving trails too bright to look at. After they pass, the ground cools quickly. A strange snow falls, the ashes from all the elements that solidify as they cool down, like silicon and iron. Mars is still a cold planet at this point. A happy side effect of this inferno is that all the water in the polar ice caps and even deep underground rises into the sky as hot steam, forming clouds that rain down over the entire planet. They would wash out the nastier gases from the atmosphere like chlorine and carry away harmful elements that accumulated on the surface. In the end, they would form shallow oceans, saltier than on Earth. We might need to do an extra cleanup afterwards. It would take about 50 years of continuous lasering to create our oxygen atmosphere. We could use this opportunity to dig deeper in some places to create the basins for salty oceans or rivers and spare some landmark features like Olympus Mons and Valles Marineris. We're not done though. The resulting atmosphere is nearly 100% oxygen and only 0.2 bar. It's hard to breathe and very flammable. To make it similar to Earth and a lot safer, we need to add a lot of nitrogen, which Mars is sadly lacking. We have to import it. The ideal source is Titan, a large moon of Saturn, covered in a thick atmosphere that's almost entirely nitrogen. We just have to move 3,000 trillion tons from the outer solar system to Mars. While that's not easy, it is doable. To process that much of Titan's atmosphere, we have to construct giant automated factories on its surface powered by our lasers to suck in the atmosphere and compress it into a liquid. This gets pumped into bullet-shaped tanks, which a mass driver shoots all the way to the red planet, where they explode and mix with the oxygen. We've already been able to send individual missions to Saturn in just a few years. With enough resources, it should be possible to complete the task within 2 generations. Of course, it would be much more convenient to have nitrogen left over from terraforming Venus on the side. We explained this in detail in another video. So, about a century after the start of the terraforming process, we have a breathable atmosphere that has the right gases. If the liberated CO2 isn't enough to warm it up to temperatures we can stand, we just add some super greenhouse gases. Mars at this point resembles a black marble from all the cooling lava, spotted with growing oceans and red patches where the old surface remains untouched. It's still a wasteland, no better than a desert on Earth. We need to fill it with life. Challenge 2. Biosphere. Installing a biosphere on a new planet is very difficult. Unexpected interactions between species or sudden diseases can destabilize it to the point of collapse. We would probably begin by seeding our young oceans with phytoplankton. Without competition, it would bloom rapidly, filling up the oceans to become the bottom of an aquatic food chain. They can be followed by tiny zooplankton, then by fish, maybe even sharks and whales. If things go well, life in the oceans will thrive. Life on land is harder. Plants need nutrient-filled ground to sink their roots into, but most of the surface is the congealed remains of lava and ash. We could wait for thousands of years for water and wind to grind it down into finer sands, or try to do it manually. But we want to be quick, and we have a big laser. Turning the beam on and off in rapid succession would cause the ground to quickly heat up and contract, which breaks it into smaller and smaller pieces. Add a bit of water and you get a sort of dark mud. Into this mud, we can mix fungi and nitrogen-fixing bacteria. They're able to absorb nitrogen and convert it into nitrate compounds to feed plants. The first plants we want to bring are native to volcanic islands on Earth, since they're perfectly suited to the laser-blasted Martian landscape. Eventually, the enriched mud becomes the foundation for grasslands and forests. In Mars's lower gravity, trees can become very tall very fast. Their roots gather the nutrients they need and then dig deeper to turn more rocks into soil, forming a self-sustaining ecosystem. At this point, we can slowly introduce more plant varieties, insects and animals. Not mosquitoes though. The new biosphere needs to be maintained to prevent it from falling out of balance. If plants grow too quickly and absorb too much carbon dioxide, the planet cools down too much. If key species die out, we could see populations collapse faster than they could recover. On Earth, other species would move in to fill the void, but our Martian biosphere is not as flexible. It takes hundreds, if not thousands of years before Mars becomes a stable environment. But eventually, the planet will have the potential to sustain large human colonies. With air, water and food available, we can finally call Mars, black, blue and green, our home. A giant volcanic island in space. Will it last though? Challenge 3. The long-term future. There is a problem we haven't addressed. Mars's core does not produce a magnetic field, so it doesn't have enough protection from solar radiation or cosmic rays. This becomes dangerous for the long-term health of Martian populations. So, as a final step, we need an artificial magnetic field. It doesn't have to be huge like Earth's, it just needs to deflect the solar wind enough so that it doesn't touch Mars. The easiest way is to construct a magnetic umbrella far ahead of Mars that splashes the solar wind to the sides. A big superconducting ring powered by nuclear facilities is all it takes. It would orbit at the Mars-Sun L1 point, keeping it constantly in between the Sun and Mars and protect the new atmosphere. And that's it. Terraforming Mars would take some work, hefty resources, and probably a century or 10, but it would be the first time we've lived in a home designed and shaped solely by us and for us. A first step towards our future among the stars. Welcome to the Kurzgesagt lab. Let's conduct a few stellar experiments. We'll first add some more mass to this protostar. More. A bit more. Wow, we've just created a blue giant, a star with 10 times the mass of our Sun. Let's now add a couple of million years and see what happens. A supernova. Breathtaking. And look, it leaves behind a black hole. Fascinating stuff. Now we record our findings. Be careful to preserve the sparkle. It's now time for Duck's final inspection. This one is always a nail-biter. He has incredibly high standards. Luckily for us, our work is scientifically accurate, offers an overview of important astrophysical processes, and is a real stunner. Duck approves. Looks like it's ready to be shared with the world as a poster. A very special piece of Kurzgesagt you can take home and touch. You can get this very special poster along with many other sciencey and spacey things created with love and care from our shop.